So at 10:35 in the UK, I would like to welcome you all to the RAS Specialist Discussion Meeting on Quasars and Galaxies on the Edge of Cosmic Reionisation. It's really great to see so many people here. I have to thank the RAS and also my co-hosts, Maxime, Trebitsch and David Lagattuta, who've been instrumental in the organisation of this meeting. And thank you everybody who sent us an abstract, because every single one of these could have been in the meeting. It's simply just the very tight time constraints, which meant we had to drastically cut this down to just 12 talks. So this was my welcome to the meeting, and David Lagattuta will be chairing this morning's session. So that's all from me for now.
All right. Well, I think you're doing an excellent job as well. Welcome everybody. Welcome to this morning's session on high redshift quasars. I'm David. I'll be chairing as has been stated. So our first speaker is going to be Roberto Mayelino, who is going to give us a review talk on high redshift quasars. Roberto is from the University of Cambridge, and I will hand the chat over to you. If you can see me when you start sharing your screen, I'll give you a little high sign at 2 minutes.
All right. Can you see the presentation?
Yep, looks good.
So, well, first I want to thank Alyssa, David, and Maxime for organizing this very nice meeting and for inviting me to give this short review. And needless to say that in less than 20 minutes, I can only touch a few topics of this broad area of research. So the first quasars around the reionization epochs are certainly exceptional objects, because while the rest of the galaxies have formed only a tiny amount of stellar mass, they are already hosted in very massive galaxies, have hypermassive black holes, and in overdense regions, so are certainly exceptional objects. And there are already a few hundreds of them discovered so far, around Redshift 6 and beyond. And while being exceptional, they are also actually normal. And this is illustrated by this spectrum of one of these quasars and overlaid with a composite of low redshift quasars, which look remarkably similar, which means that actually, despite having formed very quickly in the earliest cosmic epochs, they actually don't seem to be aware of it. And this is reflected also in the puzzling lack of chemical enrichment. This is shown here with this evolution of the ratio of the iron 2 emission to magnesium 2 emission as a function of redshift, which is taken as an approximate proxy of the iron over alpha enhancement. And despite there is a lot of scatter, but there is no evidence for significant evolution. And this is puzzling because, as you know, the iron enrichment happens by primarily type 1a supernovae on timescales which are much longer than for the alpha elements, such as magnesium and oxygen, and typically on timescales of 1 gigayears. And at redshift of 1.7, you are starting to run short of time to produce enough type 1a supernovae to produce enough iron. So you would expect these early epochs to have a drop in the iron abundance, which we don't really see. So either these emission features are not properly tracing the iron abundance or alpha element, or there is something more profound that we do not understand of these early objects. The other somewhat puzzling result is the large amount of dust in these early quasars, which is also surprising because, again, of timescales issues, because at low intermediate redshifts, most of the dust is produced by HB stars, which need about 1 gigayear to evolve. And so at these early epochs, you struggle to produce dust through these mechanisms. So an alternative mechanism for producing dust is supernova explosion and accretion in the ISM. And this can help to explain these very large dust, mass dust. But in that case, you would expect the dust in these early objects to be much different in terms of properties with respect to lower redshift objects. And quasars can be very helpful in this because they can allow for some of them to derive the extinction curve, which is a proxy of the dust properties. And at low redshift, as you see in this lower diagram, the extinction curve of quasars is well reproduced typically by an SMC-like extinction curve. But, and what you see here in black is the expected extinction curves of a family of models in the early universe. And now we have enough high quality spectra, especially for some heavily reddened quasars, especially through this nice XQR project led by Valentina Dorico, which allow us to extract the extinction curve for some of them. And interestingly, as you see, they do deviate from the extinction curve at lower redshift and seems to match within the uncertainties fairly nicely with the expectation from models, which is a very interesting and nice result. The other exceptional property of these high redshift quasars is their extreme hypermassive black holes exceeding 10 to the 9 solar masses. And these are indeed challenging to explain. This is a graph produced by Ricarda Beckman, and he is showing together with the observations where some of the candidate progenitors are expected to see in terms of redshift and mass. So direct collapse black holes, runaway nuclear star cluster, and remnants of early stars. And you see that in order to, whatever the progenitor it is, to explain these very high masses, you need these seeds to grow at a fairly high rate, close to Eddington rate, in nearly continuously in time for the entire time span between very high redshift to redshift about 6 and 7. And this is a collection of some of the simulations that have been attempted to explain these very large black hole masses. As you see, some of the most successful are those which use, not surprisingly, massive seeds, such as those produced by direct collapse black holes. But what you want to do to test these various scenarios is, of course, to investigate explore and detect and characterize quasars at higher redshifts and with lower mass, which means lower luminosities. And these will become possible soon thanks to the next generation of wide area surveys such as the Vera Rubin, Euclid, and Nancy Roman. And Daniel Mortlock will discuss this more in the later today. But of course, this will allow us to probe at higher, detect quasars at higher redshifts and also to lower luminosities. But if you really want to detect the first phases of accretion on the black hole seeds, you actually have to go even deeper. And James Webb may offer this possibility. And depending on the scenario, some of the accreting seeds may be detectable at redshift higher than 10 with the James Webb, although it still depends again, as I mentioned, on the specific scenario that you are and model that you are assuming. Even more fascinating is on the longer term is the possibility of detecting the merging of the seeds at earlier epochs through the next generation gravitational waves telescopes. What you see here in these contours are the sensitivities for detection of low intermediate mass black holes with LISA and with the Einstein telescopes. And it is amazing that with these facilities, it will be possible to detect the merging of relatively low mass black holes all the way up to a redshift of 20 and even beyond. And what you see here with these points are the emerging events as for some models of evolution of some quasars. And you see that through the detection, it will be possible to detect these various merging events according to these models, and therefore to constrain in detail what is the formation pattern of these massive black holes across the cosmic epochs. This is really fascinating prospect with the gravitational wave telescopes. Back to the present, thanks to the millimeter and sub-millimeter interferometric observation, it has been possible to characterize the host galaxy of high redshift quasars. and particularly by using the C2 line at 158 micron. And in particular, by tracing the dynamics of the galaxy, has been possible to obtain information on the dynamical mass, and finding that these high-redshift quasars are hosted typically in very massive galaxies. However, if you assume that the dynamical mass is a good proxy for the stellar mass, then what you find is that these galaxies, although very massive, are actually undermassive with what we would expect based on the black hole masses and the local black hole galaxy relation. And now there have been models which have been expecting this offset, but more recent simulations actually expect the opposite. That is, the galaxy should form faster and the black holes lag behind. So of course it's possible that the models and simulations are not implementing proper feedback or other evolutionary processes, but it's also possible that the observations are wrong or biased. For instance, we may not be measuring properly the black hole masses because we are not using the same black hole virial traces that we have in the local universe, and the James Webb again will help for that very soon. It may be possible that we are biased because we are observing primarily very luminous quasars and therefore tend to preferentially select massive black holes. And again, we will probably tackle this issue by observing lower luminosity quasars in the future. But another possibility is that the dynamical mass is not properly determined because of inclination effects, or is not a good proxy of the stellar mass. And hopefully soon the James Webb will allow us to detect the host galaxy or the stellar light of the host galaxies in a number of quasars, especially by using the integral field spectroscopy, because the spectral information helps in this process. And by this simulation of one of these putative integral IFS observation with James Webb, where the quasar light has been subtracted. And this is a simulated started spectrum where you can obtain information not only on the stellar mass, but also on the age and other properties of the stellar population. Of course, in the longer term, the advent of even larger telescope, in particular the ELT and similar, will have a much higher angular resolution and therefore may provide us to disentangle the quasar light from the stellar light even with higher accuracy. Another interesting prediction of simulations is that the host galaxies of high-redshift quasars should be very bulgy. And I can't resist from showing this recent result published today actually on Science by Federico Lelli, where we used the very high sensitivity and the high angular resolution observation of C+ of a slightly lower redshift quasar, obscured quasar at redshift 4.7, where with the kinematics clearly showed the detection of a very massive bulge in this primeval quasar, very much in line with what was expected by the simulation. One clear result, however, is that these early quasars are hosted in massive galaxies, and they are the best potential progenitors for massive galaxies at lower redshift. And in particular, are probably the best putative progenitors for massive, passive, and old galaxies that are already found to be in place by redshift around 2 and 4. Now, the fact that these high redshift galaxies are already old at these early epochs, it means that star formation quenching must have happened before redshift of 6. And of course, the most plausible culprit for this quenching is efficient quasar feedback at these early epochs. And so there have been various studies attempting to find this evidence for quasar feedback at redshift higher than 6. And the detection of cold winds, quasar-driven winds, has been one of these main topic of research. But there have been some apparently conflicting results, which are summarizing these two cases here. So this study in which I have been involved on the left is the stacking of nearly 50 quasars, where reaching high sensitivity, it was possible with a C2 line to detect very broad wings with velocity up to 1,000 km/s, which are interpreted as a massive quasar-driven cold wind. At the right, you see a similar stack, which reaches essentially the same sensitivity as this other stack here, but in which there is no evidence for these broad wings associated with putative quasar-driven outflow. So this is puzzling, but actually I think that both results are correct. It seems that when we deal with interferometry, the word sensitivity must be taken, given properly, in the sense that you have to specify on what scales you have the sensitivity. In particularly in this study, although in both studies they use a variety of ALMA configurations, in this case the bulk of the deepest observations are at high resolution, while in this case, in the case of the Bischetti study, most of the observation adopted are at low resolution. So, and as you can see from the different beams, resulting beams in the stacks. So each of these two stacks are sensitive to different scales, okay? And this is quite relevant for the outflows, because outflows tend to be by nature extended. And I illustrate this in this simulation where I take the, we take this model here, started from this observation here, where we have a compact starburst and an extended outflow, similar to what observed in Bischetti, and observe the same identical object with the same exposure time, but and reaching the same sensitivity per beam in the two cases. And of course, in the low resolution case, you detect the broad extended outflow with the broad wings, and in the other case, you cannot, of course, detect the extended outflow. So essentially, both results are true, are simply telling us different information on different scales. And the bottom line is that, of course, to detect this extended outflow, you need to use specific observation sensitive to very large scales. However, even if you have these cold outflows, the interesting result is that the energetics associated with these cold winds is actually very low, or the order of less than 0.1% of the Agn luminosity. And these kind of energetics are not what are expected for quenching star formation in quasar host galaxies. You need much higher, much more energetic outflows. So one possibility is that most of the energy of these outflows is in the ionized phase. And there is some indications that this may be the case, because there are studies showing that at high redshift, these very powerful quasars have highly ionized velocities traced by highly ionized lines, which are much higher than the lower redshift counterparts, which goes in this direction. Our host, Alyssa, has detected a number of laminar halos around these high redshift quasars, which are characterized by very large velocity dispersions with widths approaching 1,000 km/s, which may be tracing actually outflows, highly ionized outflows as driven by these quasars. And keep in mind that, again, these kind of high velocity dispersion are not observed typically in lower redshift quasars. Another interesting result is that it seems that at redshift higher than 6, the fraction of broad absorption light quasars, that is, quasars which have prominent absorption, highly blue shifted features associated with highly ionized outflows along our right side, the fraction of these bulk quasars is significantly higher than at lower redshift. It's not the case that the most distant quasar discovered so far is actually one of these bulk quasars. And a recent study based on the XQR30 project, which has very high quality signal to noise, very high signal to noise spectra of 30 quasars, they find that about 1/3 of these high redshift quasars have Ball features versus about 10% at lower redshift. Not only, but these Ball quasars are characterized by very much higher outflow velocity than the lower redshift quasar. So it may really be that you have more prominent ionized outflow in this early quasar than at lower redshift. However, to properly characterize their energetics and outflow rates, you need to spatially resolve these outflows, possibly by using emission lines in the optical rest plane. And for this, we will have to wait for GWST. Now, even if neither cold nor ionized outflows work in terms of explaining the quenching by quasar-driven outflows of early galaxies, then it may simply be that quasars are indeed ineffective in quenching star formation at high redshift. And this may be what Maxime has found in these simulations here, where in these early galaxies, regardless of whether he puts an Agn or not, it doesn't seem to affect significantly the evolution of the star formation rate in these systems. So if that's the case, then we have to find another mechanism to produce massive and old galaxies which are already in place at redshift between 2 and 4. And these is my summary, which is just a couple of bullets points. So there's been fantastic progress in the last 20 years, and especially in recent years, in characterizing and finding quasars around their reionization epochs. There are still a lot of open questions to be tackled, which I think is the exciting and fun part of this, because otherwise it would be too boring if we had understood everything. And that the near future, and by near I mean in the next about 10 years, is expected to be even more exciting thanks to the forthcoming facilities that will enable even more progress to be made in this area in the coming years. And thank you.
All right. Thank you very much for that, Roberto. That was very interesting. If there are any questions, feel free you can post them in the Q&A or on the Slack. And Maxime, I think, will be checking for questions. So
yeah. So we have a first question from Ricardo Beckman saying, there has been a few papers lately showing close companions or possibly ongoing mergers for the host galaxies of high redshift quasars. Do you think that mergers play an important role for high-Z quasar?
Yes, it did. Indeed, this was one point that I didn't have to point. So, for instance, these result published today on Science shows actually very regular rotation curves without any evidence for merging, which is, however, it looks like a local galaxy, if you wish, in terms of rotation and even velocity dispersion. But a number of quasars at high redshift show evidence actually for much more disturbed kinematics and morphology, which hints at the presence of ongoing merging or anyhow disturbed morphology and kinematics. Didn't have time to mention this. And I think we will hear more about this in a talk later this morning. And yes, this is probably merging do play a major role, and this is we are seeing that again in the dynamics and morphology, and is an exciting prospect also for the detection of gravitational waves. We will test a clear test of their importance. I think will come specifically from the detection of gravitational waves with LISA specifically. Yeah.
okay.
Do we have time for one more question?
Yeah, I think we can do one more.
Okay, then Richard Ellis asked via the Q&A, today's result on the presence of a bulge in QSO host galaxies at redshift 5 is very exciting. Can you estimate the central velocity dispersion, and if so, what does it imply?
Yes, it's. I don't have the figure here with me, but it's very small. It's a very cold disk throughout the disk. I think also in the center, and the velocity v over sigma is about 10, which is very high. It's essentially the same ratio that you see in local galaxies again, and which is unusual for these high redshifts, where we know that the V over sigma tend to plummet to much lower values. So it's not clear why, if this is peculiar galaxies or whether there's been observational bias in previous observations. There is a program that is ongoing that is aiming at testing exactly this with more galaxies.
All right, great. Well, let's virtually thank Roberto again for the talk, and we can move on to our next speaker. So our next speaker is Daniel Whalen from IGC Portsmouth, who will be talking about the first quasars in the universe. And whenever you're ready, Daniel, take it away.
You're muted, I think.
I think you're muted, yeah.
Mute.
There
My
we go.
apologies.
No worries.
Okay. Okay, well, again, thanks to the organizers for this opportunity to discuss our recent numerical simulations on the formation of the first quasars in the universe at every stage of their formation, and our synthetic observables in the near infrared and radio. So let me go ahead and get started. As Roberto already discussed, there are two main seed pathways for the formation of quasars above redshift 6. So one possibility is that they formed out of normal population 3 star black holes at redshift 25. These black holes were typically a couple of hundred solar masses at birth. But to get to 1 billion or even 2 billion solar masses by redshift 7, those black holes would have to accrete at very nearly the Eddington rate the entire time down to redshift 7. And several numerical simulations have, in large cosmological boxes, have shown that that's rather difficult. And so I would say that the leading contenders right now for the seeds of the first quasars are so-called direct collapse black holes. And these direct collapse black holes form in primordial halos that grow to 10 to the 7 to 10 to the 8 solar masses without having previously formed a primordial star, either because they were immersed in very strong ultraviolet backgrounds that suppress star formation, or they were immersed in supersonic baryon streaming motions. They're thought to be remnants of basically baryon acoustic oscillations in the early universe. So there are these supersonic sloshing motions between gas and dark matter in the halo that can also delay star formation. And so I'm going to focus on the formation of massive black hole seeds in atomically cooled halos. So atomic cooling, Lyman alpha cooling, triggers what we sometimes call catastrophic baryon collapse at the centers of the halos, and gas collapses to the centers of the halos at up to a solar mass per year. And until really 2013, we didn't know what that gas became, whether it simply got hotter and denser and was abruptly enveloped by an event horizon without having ever experienced the main sequence, or if it became a main sequence star. And so here, if the movie runs, this is an ENSO numerical simulation of what happens to gas at the centers of one of these halos when it collapses through atomic cooling. As you can see, it forms a very massive accretion disk. It typically feeds gas to the center of the disk at average rates, in this case, of about 0.4 to 0.5 solar masses per year. And these rates persist for long times. So very recently, we've discovered that it was originally thought for a long time that only single direct collapse black holes or supermassive stars would form at the centers of these halos. But now, with recent simulations evolving collapse in these halos out to much larger times, we now routinely find the formation of massive binary disks, both of which are capable of forming supermassive stars. And these disks often merge after 1 to 2 million years. And so this opens up, the tantalizing possibility of direct collapse black hole mergers, for example, that could be found by Lisa. So what we find in the stellar evolution calculations is that these rapid inflows build up typically red, cool, bloated hypergiants. And these objects can be the diameter of the solar system. And while they're cool, they're still extremely luminous. They can be up to 10 to the 10 solar luminosities. And so even though they're cool, they can still have a significant flux redward of the Lyman alpha limit in the rest frame that can be found today by, for example, the James Webb Space Telescope, or in principle by WFIRST. And so here, my student Marco Sorace calculated near-infrared magnitudes for supermassive stars, rapidly accreting supermassive stars forming in these halos. And as you can see, with James Webb, if James Webb came across one of these stars in one of its narrow fields of view, it could detect them with NIRCam out to about redshift 14 to 15. So, but the key is that its narrow field of view would have to come across one of these objects. It would be much more advantageous if one of these stars could be detected by Euclid or WFIRST with their much wider near-infrared fields. But unfortunately, as we can see here in the H and J and Y bands, the prospects for direct detection of supermassive stars by WFIRST or Euclid are rather slim, because they're below the detection limit of any planned wide field survey now. Now, this does not mean that Euclid and WFIRST could not detect these objects in wide fields, and I'll come back to that in just a moment. But here is the bottom line for direct detections of the supermassive stars. So one thing I'll mention quickly is that very massive direct collapse black hole seeds, and when I say supermassive stars, I refer to stars that collapse at about 100,000 solar masses or a little above at the end of their lives. Those only happen in quite strong Lyman-Werner ultraviolet backgrounds. If one has more modest Lyman-Werner backgrounds, we get a third branch of primordial star formation that's intermediate in mass between the very massive normal POP3 stars that form at redshift 20 to 25 and the supermassive objects that form between redshift 15 and 20. And that's due to hybrid atomic and molecular hydrogen cooling in the halos. And just very briefly, new numerical simulations by my student Sam Patrick and others show that kind of collapse will result in POP3 stars that are typically 2,000 to 5,000 solar mass stars. And so there is a third tier, I would say, of quasar seeds at high redshift in mass. Now, the formation of a direct collapse black hole by itself doesn't guarantee a redshift 7 quasar. That direct collapse black hole has to be born at the nexus of either cold accretion flows capable of fueling its rapid growth, or in a merger that's in a halo that's destined to undergo multiple mergers with other gas-rich halos. And so we perform numerical simulations of the former, basically the growth and evolution of a direct collapse black hole in a cold reservoir of gas that reaches about 1 trillion solar masses by redshift 7, primarily through cold accretion flows. And very briefly, those were done with the ENSO adaptive mesh refinement cosmology code. That simulation had X-ray feedback from the black hole. It had supernova, wind, and ionizing UV feedback from star formation in the host galaxy of the black hole. And so we performed simulations of the evolution of the black hole. And as you can see here, there's an image of the direct collapse black hole at birth, X-rays coming out. We calculated source frame spectra using the cloudy code. And what we found is that the prospects for direct detections of quasars at birth, direct collapse black holes, with James Webb are better than finding supermassive stars. These objects will be brighter in the near infrared. And interestingly, they'll be bright in the MIRI bands, the mid-infrared. And that's very fortunate for us, because this is one quick and simple way we could distinguish a direct collapse black hole at high redshift from its supermassive progenitor star. And as you can see, NIRCam and James Webb would be able to detect these objects out to redshift 20 at birth. Again, if it came across one. Again, unfortunately, the prospects are less likely for direct detections of these objects in wide fields where you have a much higher likelihood of coming across one by Euclidean W first. However, as I mentioned earlier, that doesn't mean that these objects won't show up in Euclidean W first, because these wide fields will enclose thousands of massive galaxies and galaxy clusters capable of strongly gravitationally lensing from flux from background black holes and stars, in principle above the detection limits of currently planned surveys. And so here, this is very preliminary data, but here what we see is the number density of either direct collapse black holes or their supermassive stellar progenitors required for Euclid or W first to pick one up in current surveys between redshift 7 and 15. And as you can see, if we compared these number densities to the theoretically predicted numbers of black holes per cubic megaparsec at high redshift, these wide field surveys could detect hundreds of these objects out to redshift 15. And very briefly, let me just mention that we do expect radio power from direct collapse black holes, and SKA should be able to detect flux at the low end of its range from these objects out to about redshift 8 to 9. So it'll be harder to find these in the radio. And then finally, let me conclude my talk with this plot here. This is the H-band luminosity for Euclid for the halo, for the black hole that we modeled in our ENSO simulation. And that black hole was seeded with a DCBH at redshift 19, and it reached 2 billion solar masses by redshift 7 in the simulation. And its properties and the properties of its host galaxy were nearly an identical match to those of the 2011 quasar found by Daniel Mortlock. And so what this loss plot shows us is that as the DCBH turns into a quasar, evolves into a quasar, we should be able to detect it out to redshifts 13 and 14 directly by Euclid. And I think that this is an exciting result because synergies between Euclid W first, James Webb, and the ELT will really inaugurate the era of redshift 5 to 15 quasar astronomy in the coming decade. So thank you very much.
All right, thank you, Daniel. I think we have time for one question, maybe, Maxime?
Okay, so I don't see any apart from mine so far, so I will use the privilege to ask my question, which is related to the, oh, sorry, there is one from Dan Mortlock, so maybe that's better. The evolution plot showing the match of the redshift 7 quasar is very promising. So was there significant tuning required to get the agreement between the two?
No, actually, there was no adjustment of feedback parameters necessary to achieve that agreement. So very briefly, that simulation was able to resolve star formation in the host galaxy of the black hole. And so we didn't have to have any subgrid prescriptions, for example, for supernova feedback or ionizing UV feedback from those star forming regions. The only subgrid prescription we had was for accretion onto the black hole itself, because we couldn't resolve the accretion disk of the black hole, so we assumed an alpha disk model. So this was not like a tuned simulation, for example, like we find with Eagle and Illustris, who are after the Magorian relationship at redshift 0.
So if that's fine with David, I will just jump on this to like ask you a bit further. There must still be some factor of luck that the halo mass, for instance, is in the right range to get this kind of black hole, right?
Yes, and so if we looked at for example, we looked as a sanity check at the ratio of star-forming gas to the halo mass itself. And it was consistent with the usual Baruzzi et al. Calculations, his halo calculations at high redshift. So, however, the black hole itself, its mass is above the usual Magorian relationship. So it was heavier than one would expect from the Magorian relationship at redshift 0 for the halo mass that we had.
Okay, thanks.
Great, thanks very much for that. So we can move on to our next speaker, who is Roberto Mayelino at INAF in Bologna, and I'll, if you're not already unmuted, maybe unmute yourself now before you start sharing screen, who will be talking to us about a supermassive black hole at cosmic dawn and the large scale structure around it.
Can you hear me?
I can, yes.
So thank you. Thanks I'd like to thank the organizer for allocating this contribution. So I'll be mainly talking about the results we obtained during the past fall and that have been published in this paper by Marco Mioli, a colleague in Bologna, and that has been also the subject of an ESO press release this past fall. So the talk is about finding overdensities of galaxies around the early quasars, in particular about the first spectroscopic confirmation of such an overdensity. We heard briefly from Roberto this morning that the big supermassive black holes we observe at redshift 6 are likely to be formed and grown within large dark matter halos. We have several arguments to say so. First of all, the mass of their host galaxies well in excess of 10 to the 10 solar masses, which means that if one applies standard halo to stellar to halo mass ratio, it would mean that they live in halos as massive as 10 to the 12 solar masses or so. Another element that let us think that these supermassive black holes live in very deep potential wells is the fact that many of them, about half of them, have a companion galaxy within a distance of 100 physical megaparsec. And this is a result that came out from ALMA observation. So again, they likely live in halos with masses above 10 to the 12 solar masses or so. Theory is telling us that because of the large gas reservoirs and also because of mergers funneling gas towards the black hole center is much easier, sorry, in overdense environments, and also the host can grow very quickly. So even from theoretical simulation, we can see that quasars form preferentially in such massive halos. And again, because of the mass of the halo, we expect that this is embedded within large-scale structures that extend for a few physical megaparsecs. So this is an example taken from simulation by Tiago Costa some years ago. Here you see an overdense region with all the structure extending for a few megaparsec made of black holes and galaxies, and this is what is seen in an average density region. So one may expect to see significant galaxies over densities around early quasars, but the search so far has been inconclusive. I have to say that most of these searches have been restricted to about 0.51 physical megaparsec within the black hole. And in this scale, even simulations say that you may expect a large variance in the number of galaxies you may detect because, for instance, of feedback that can arise both from the AGN and also from supernovae exploding within the structure. So if one considers, for instance, the radial profile of the overdensity in the inner regions where the maximum of the overdensity should be expected, this could be really depressed because of feedback effect. And so maybe if one try to observe at larger scales above 1 physical megaparsec or so, then one may hope to detect overdensities of the order of a few. And actually, we know that such very extended structures for a few physical megaparsec, 5, 6, 8 physical megaparsecs do exist and have been observed, not around early quasars, but still they have been observed at Redshift 6, for instance, in wide area surveys. So our idea was to try to sample regions at large scales around quasars. At the beginning, we selected a sample of 4, and then we concentrated on the one that was most promising. And in particular, we observed a field that is about 8 by 8 physical megaparsec around the quasar SDSS J1030 at Redshift 6.3 with the LBT and also with other instruments providing near-infrared coverage. And in this field, by means of standard high band dropout selection, we selected about 20 LBG candidates at the quasar redshift that already provided us with good evidence for an imaging over density of the order of 2.4, significant at 4 sigma, within 5 physical megaparsec from the quasars. Obviously, this was an imaging over density. The selection function of high band dropout covers a redshift range that is very large, so this needs a spectroscopic confirmation to get the distance, the actual distance of the candidates. So we started over the years a program at 8 to 10 meter class telescope to follow up these objects spectroscopically. You see here again the field, and you see here the objects that we were able to confirm spectroscopically at the quasar redshift, together with the other observation in the inner part of the field that came from archival MUSE data. So on the right, you see an example of such an LBG source confirmed at Redshift 6.3. We observed a break in the Keck Deimos data, and this break at 6.3 was then confirmed by millimeter spectroscopy using NOIMA. We were able to add more candidates at Redshift 6.3, get more redshifts. In particular, at the end, we got 4 LBG confirmed at Redshift 6.3, plus 2 Lyman alpha emitters coming from MUSE, very close to the black holes. And here on the right again, you can see a couple of examples of spectra coming from our campaign. Here you see a spectrum at Redshift 6.32, and also you can immediately judge the difficulty of getting effective Lyman alpha measurement at this redshift because of skylines. And in particular, I'd like to emphasize that if Lyman alpha was at 6.33, it would be missed, for instance, because of these strong residuals in skyline. So in the end, as I said, we got 6 galaxies within this redshift range, which corresponds to radial distances from the quasars of about 5 megaparsec, which is the extension, the transverse extension of the structure. So if we look at the redshift distribution of these sources, we obtain the following histogram. So what you see here is the whole distribution of the redshifts that we derived. We didn't get any low redshift interlopers. That is a good sign that the selection has worked well. And in the distribution, we do see a clump of objects at 5.7 and a significant peak at around 6.3. This lower redshift clump is expected because of the selection function of high band dropout. You can see the gray curves here, which peaks around 5.7. But this is more significant, and it was not expected given the selection function. And if we try to estimate its significance, it is about 3.5 sigma, which we think is a conservative estimate. So by considering these 6 objects in this spike here as members of the structure, we measure an overdensity, which is of the order of 1.52, which is fine with what is predicted by simulations, that is distributed over a volume of about 800 physical megaparsec cube. And again, thanks. And again, if we consider this overdensity level and within the probed volume, we can try to convert this measurement into a halo mass measurement through standard recipes for quasar LBG cross-correlation clustering. And we derived a halo mass for the quasar, which is above 10 to the 12 solar masses. You can see the details in the paper. So this is the main result of our effort. So the field around the J30 quasar features the first spectroscopically confirmed galaxy overdensity around an early supermassive black hole. And we think that maybe all the failures in other quasar fields are maybe likely related to observational limitation, either on the scale sampled or on, again, on the type of observation that have been performed. So what is next? Well, first of all, it is necessary to move from the discovery of this structure to the physical characterization of this overdensity in the field of J1030, but also it is mandatory to discover other similar large-scale structures around early supermassive black holes using, for instance, ALMA, James Webb, or forthcoming facilities. And as an example of such efforts, in the same field I described above, we have now more time approved for imaging to go deeper by 1 mag, and we expect to detect about 130 I-band dropout overall in the field. One possibility to get member of the overdensities through ALMA millimeter spectral scan, which is a promising way to detect carbon-2 line and confirm galaxies at that redshift. And also, obviously, James Webb will have much to say about this issue. And in particular, this field, together with other 5 fields, is included in a GTO proposal with the goal, among others, of probing the overdensity through oxygen 3 and H beta lines at redshift around 6. And I thank you all, and I have concluded.
All right, thanks very much for that. We have time for maybe a question or two.
Okay, so our first question was from Michael Strauss, asking if you can explain a bit more why you decided to focus on this specific quasar. Is it like any peculiarity from the quasar itself, or just an unusually large overdensity or something like that?
Yes, this quasar was known to have a 3 sigma overdensity based on previous HST observations. But also when we performed our large-scale observations with DLBC at DLBT, again, this field was found to be the most overdense. We also found overdensities around other quasars, but not as significant as this one in imaging. And so this was the first that we looked at.
Okay, thanks. One more from Elizabeth Stanway, wondering if you're confident you found the edge of the structure or not.
Sorry, if we found the edge of the structure.
You have the full size of the overdensity, or?
No, I don't think so, actually. If I just go back to this plot, you see that there is this concentration, which is on the northwest part of the image. And so it is probably likely that if we extend the observations on larger scale with a few more pointings, this part is probably expanding further. So I do not really think we have observed the whole structure. In particular, we didn't get to the average density field with our limited field of view. So it may be well extended for 10 physical megaparsecs or so.
Okay, thanks.
Okay, great. Thanks very much for that again. Let's now move on to our final speaker for this first session, and that is Rebecca Bowler at the University of Oxford, who will tell us about the faint end of the UV luminosity function of Agns at high redshift.
Yeah, okay.
Okay, looks good.
Yeah.
And take it away.
Great. So thank you to the organisers for giving me the opportunity to talk today. I have to say I'm feeling quite nostalgic for overpriced London coffee today, but hopefully soon we'll all be back together. So this talk is about a paper which was accepted earlier this year, along with Nathan Adams, Matt Jarvis, and Boris Hausler. So the context of this project was really based on the fact that until quite recently, at high redshift, when thinking about populations of sources, quasars and galaxies have been treated quite separately. So this is mainly due to the quite disparate spaces used to select them. For example, quasars are very rare, so we use very wide area surveys to find them. Oops. Whereas galaxies are much more numerous but fainter, with their UV luminosity dominated by star formation, which means we tend to focus on the faint end via very deep pencil beam surveys. So quite naturally then, these sort of surveys have started to converge now with studies of faint quasars and of bright galaxies. And this intermediate luminosity range is really interesting to answer several quite fundamental questions. So we want to know, what are the properties of these sources? Are they sources in which the UV luminosity has got some component from both the active black hole and the star formation? We can use this regime to study whether ultraluminous star-forming galaxies exist at these very high redshifts. And also, the focus of this talk, we can try and understand what is the faint end slope of the AGN luminosity function. So how many of these faint AGN are there? So as I said, people are starting to converge, and now at Redshift 4, for example, we have really nice samples that cover both these regimes. So this is work done by my PhD student, Nathan Adams, published last year. And this is the Redshift 4 luminosity function he derived, shown as the red point. So you can see it nicely bridges these two populations. What you can maybe already see from this graph then is that there's quite a large uncertainty in what the faint end slope of the luminosity function is for the AGN. Some high redshift AGN surveys have found quite a flat slope, like this Akiyama, these triangles here, while others, including Nathan, have found the possibility of it being quite steep from simultaneous fitting of his data. And the reason why this is important is because there's been quite a lot of discussion recently about what is the contribution of these faint quasars to reionisation, and this faint end slope is a crucial component of that calculation. So in this work, what we did was we took Nathan's sample, bridging these two populations, and supplemented it with additional data to try and understand the properties of these intermediate luminosity sources. So we first looked at the morphology using this amazing Hubble I-band mosaic over the cosmos field. And we also searched the archive for spectra of objects in this luminosity range. So firstly, the morphology results. What we found was that, as expected, the very brightest sources in our sample, which are quasars, show a very compact point-like morphology. The faintest sources in the sample show what we expect for star-forming galaxies. These are irregular, clumpy objects that are very clearly resolved in the Hubble data. And in the intermediate luminosity regime, apologies, this figure is somewhat overwhelming. What we found was quite interesting. We found a mixture of point-like sources and these very highly extended star-forming galaxies. And this is also evident in the size-luminosity relation. So if we derive the size-luminosity relation at high redshift, we find that brighter sources are larger, typically. And then we're also able to notice this very, very dramatic drop in the size, which is due to this increasing impact of these point source AGN-dominated sources. In the archival spectra, we found a very similar story. On the upper left here, you see the very brightest objects in our sample. These all show very clear quasar-like spectra. At the faint end, we see galaxy star formation dominated spectra, where we have absorption lines and narrow Lyman alpha. In this intermediate luminosity regime, we see a mixture of the two type sources, including some very luminous objects which appear to be dominated by star formation and some somewhat fainter quasar type sources. So what we then did was to combine all this information into the Agn fraction And now this assumes that sources are either one or the other of these two categories. And this is typically what we found in our data. So we derived Agn fraction from the morphology and from the spectra. And interestingly, we found slightly higher Agn fraction to fainter luminosities from the spectra. So we can then use this Agn fraction to separate the ultraviolet, rest-frame ultraviolet luminosity function at redshift 4 into these two components, Agn dominated and star forming dominated, which you can see as the two lines on here. Now, because we had two measurements of the Agn fraction, we could do it two ways. And reassuringly, if we use our morphology measurement, so basically, is the source resolved or not, we find very good agreement with the study of Akiyama, shown in the gray points here. And this is to be expected, as they also used a kind of size point source criterion in their selection. If we use the spectra to separate the luminosity function, as I showed you on the previous slide, we find a slightly higher Agn fraction at fainter luminosities. And this means that we tentatively derive a steeper slope for the Agn luminosity function when using the spectra. So what does this all mean? Can we bring it all together? And the first thing to do in bringing these results together is to ask, what do we expect the faint end of the slope of the Agn luminosity function to be at these high redshifts? And interestingly, several empirical models predict that it should be actually rather steep. And what we did in the paper was to make a toy model just to kind of explore these effects. And we also reproduced quite a steep faint end slope, shown as the solid black line here. So if we take our sort of toy model for the Agn luminosity function and simulate a point source selection, like we would do in these faint Agn studies, so we only classify something as an Agn if it is basically a point source, then what we find is we can reproduce the flattening that's observed in these other studies. Now, the reason why this happens, so that's shown as a blue dotted line here, which you can see matches the gray points. So the reason why this happens is because as we get fainter, there's an increasing effect of the host galaxy light. And this means that Agn searches that imply that the source has to be a point source become incomplete as they go fainter and fainter. Now, this is really exciting prospects for upcoming wide area multi-object spectroscopy surveys, because these will be looking identifying Agn not just via their size, their point source nature, but also by their weak spectral features potentially embedded in these host galaxies. So I may have gone slightly too fast, apologies, but this is my take-home message for this talk. Our results imply that point source selections for faint Agn are incomplete in the rest frame UV, and this is due to the impact of the host galaxy. And what this does is it leads to an artificial flattening of the faint end, as found by several studies. And our data in this toy model indicate that the underlying slope could be quite steep, around -1.8. Now, this could be seen as potentially evidence for an increased contribution of Agn to reionization. However, this is not what our results suggest, because although the slope could be steep, the normalization is much lower than you need to have a non-negligible role of Agn. Sorry, I shouldn't have used that word at the end, in reionization. So our results still suggest that galaxies are the main drivers of this process. And with that, I'll end.
All right, thank you very much for that. Maxime, any questions so far?
Yes.
Looks like one has just popped up.
One on the
Thank
Q&A
you.
by
Yes.
Rodrigo Vezia, wondering what fraction of the point sources are expected to be unresolved starbursts, like we see in the local extreme UV starburst population, typically green.
Yeah, that's a great question. Hardly any, because as I showed in that kind of large grid-like figure, what we find is that because of the size and luminosity relation, the brightest galaxies, which could be confused with faint Agn, are very highly resolved at this magnitude. So they're, I don't know the exact fraction, but I'd be surprised if any of those would be point source, appear as point sources.
Do we have time for one more, David?
We can do one quick one.
So there is one from, well, there are two, but there is one from Fabio Vito wondering if you've compared the UV luminosity function faint slope at redshift 4 with the X-ray luminosity function slope, because the XLF should be less sensitive to star formation contamination and doesn't rely on morphological selection.
I have had a look at that via these empirical studies that tend to predict quite a steep fainting slope. So I think the slope is consistent, but I don't know any more details than that. I can have a look on the Slack and answer more.
All right, great. I think, yeah, in the interest of time, I think we can finish this session now. So let's virtually thank all of our morning speakers again, or at least the speakers of the first session. And I will now hand it over to Alyssa, who will be chairing the next session.
Thanks, David. Okay, this is going really well. We are running 5 minutes late, but I think that's not too bad given the circumstances. So thanks everyone for a good morning so far. Encourage everybody to keep talking on the Slack. It's very active, which is great. Okay, so moving into the Galaxies at High Redshift session, we now have our 20-minute review from Steve Wilkins, who is reader and head of astronomy at the University of Sussex.
Thanks, Alyssa, and it's great to be virtually here and see some people at least today. It's a shame we're not in Burlington House right now. So today I'm going to give what turns out to be a very broad general introduction to the high redshift field, and this is partly because the field is very large, but partly because I know these meetings have in the past attracted kind of more general audience than people just in this field. So I thought it might be useful just to outline some of the big questions and some of the big prospects of the future. So today I'm going to give this very broad overview. I'm going to continue to use this first light and reionization epoch because I love acronyms like all astronomers, and as a way of inception you into a project that I'm working on as well, which I'll mention later. So I'll very briefly talk about some of the context here, then talk about some of the observations, and then I'll try and spend a little bit of time just outlining some of the different simulations and modeling approaches that we have available to us at the moment. I'd just like to say that this presentation doesn't have a huge amount of support from references to literature, for example. This wasn't deliberate. This was really just the pressures of the pandemic eating up all of my time over the last month when I've been trying to do this. So we're probably all familiar with this type of diagram, but I'm going to annotate it myself in a second. So here we have the history of the universe on a somewhat sneakily chosen logarithmic scale, although not quite. So we see at the end, it doesn't really work anymore. But this is really to emphasize the bit of the universe's history that hopefully most of the people in this group care about. So I'm just going to go through and annotate. So if we go all the way back to the Big Bang in the first fraction of a second, we're still at the point of Herbie dragons. So we suspect that inflation took place, although the exact physical mechanism which drove it we're unclear of. Obviously, prior to inflation, we have very little evidence of what happened then. Again, many of my cosmologist friends would argue with me, but the subsequent few 100,000 years are almost solved in that the physics seems to become a little bit simpler. So then we get up to the era of recombination, obviously where we get the CMB from. We're then going to move into the Dark Ages. And I'm not going to talk very much about that, although it overlaps with this topic. And that's because the Dark Ages is really the realm of 8.3 inch or 21 centimeter science probed by things like LOFAR and SKA. That's such a large field that there's really no justice I can do to it by even saying very much. And if we go over here, again, this is a little bit tongue-in-cheek, but kind of the later stages of galaxy formation are a little bit better solved. And where we're lying today is right in the middle here. So what I like to call the exciting science, or this first light and reionization epoch. So what are the key events that happened during this period? So this is the very first era of galaxy formation, encompassing the first era of star formation as well. So this era kind of extends from the first star formation about redshift 20, could actually be more like 40, all the way to the end of reionization at about redshift 5 or 6. and this encompasses several major events. Okay, so obviously the formation of the first stars from the primordial gas, the early enrichment of the universe and thus the transition to population 2 star formation, the production of the first dust, the hydrogen reionization of the universe, with helium reionization occurring a little bit later, the formation and early growth of supermassive black holes, and possibly the formation of actually the first quench or passive galaxies. So it could be that even during this very early period, we're starting to suppress star formation in some of these galaxies. Okay, so we could articulate this in a different way and just maybe mention some of the open questions in the field. So how, when, and where did the first stars form, and how are they different, for example, in terms of their IMF from population 2 star formation? How long did this persevere? Did it persevere for longer in different areas of the universe than other areas? How, when, and where did the first supermassive black holes form, and what was their contribution towards reionization? We just heard from Rebecca that perhaps the contribution to reionization is still expected to be quite small, although I would caveat that we don't really know what the escape fraction is of AGN and galaxies. So more generally, what was the source of photons responsible for reionization, and how does the ionizing emissivity and the escape fraction depend on galaxy properties? Okay, this is one of the big questions that we'd like to answer. How was the early universe enriched with heavy elements, and how much was locked up in dust? Because of dust, how much star formation is missed? So how incomplete are our observations of this part of the universe's history? And how and when were the first galaxies quenched? And did this take place relatively early in the universe's history, like there are some tentative observational results suggesting? So perhaps a controversial statement, but I think these questions can only be fully answered with the combination of observations in theory and specifically simulations. So I'm going to try and cover both these areas really quickly today. So observations of the flare. So again, I'm not going to talk very much about 21 centimeter observations, but I just thought I'd dump this here, that we can get insights into this era and particularly the dark ages from 21 centimeter observations. This is really the realm of things like LOFAR and in the more distant future, SKA and its precursors. Okay, so this will have a tremendous impact on our understanding of the field. But I'm going to talk more specifically about individual galaxies and maybe their environments, by which I mean the local CGM, the IGM, and whether there's any clustering. So observations of galaxies in this era do light the frontier of our capabilities. That's because these objects are typically intrinsically faint, so they haven't had time to build up large reservoirs of stars and gas. They're obviously very far away, so we have a large luminosity distance. And crucially, they're redshifted into the infrared. So this makes them more difficult to observe from the ground. In the infrared, we have poorer sensitivity, and we generally have a lack of facilities as well, in particular spectroscopic facilities. So this requires that we exploit all of the state-of-the-art facilities that we know and love. So this is a little slide pulled from some of my teaching, but here we have some of the current observatories that we frequently use to study this period of the universe's history. And you can see here we've got Hubble, which is still going after 30 years. We have the VLT and other large ground-based telescopes. Vista, there's a lot of work being done on this recently. Spitzer, the little telescope that could, which trundled on until early 2020 and continued making advances, particularly in this field, right until the very end. Herschel, which was this brief star that shone and allowed us to see the kind of high mass, high star formation rates at very highest redshifts. And now ALMA, which goes ahead and completely destroys my diagram here by kind of dominating the total area. So you can see each of these are the individual ALMA dishes here. So what exactly we can learn from observations depends on the characteristics of those observations, so including their area, depth, their wavelength coverage, and to some extent their spectral and spatial resolution. So I'm just really going to summarize a few of the key observations that we've obtained over the last 10 years. So maybe we can look at the wavelength axis first of all, and we can look at just a simple SED of a galaxy. So we have here a typical star-forming galaxy. I've redshifted it to around redshift 7. So where the rest frame is in the UV, we're now seeing it in the near infrared at redshift 7. And so we can see here that we have the rest frame UV, which is largely coming from the hot stars and the AGN. We have the ionized gas, which again is driven by the hot stars and the AGN. In the rest frame visible, obviously we have the contributions from normal stars. And as we move into the far infrared, now we start getting the contribution from dust, but we also have various molecular lines that we can exploit to learn about the gas. Okay, so we kind of have this picture here. So, but what specifically have we learned about high redshift galaxies across these wavelengths? Now, actually, we're able to probe just about all of these wavelengths with current facilities or with recent facilities. So we can obviously start off over here in the UV. This is where arguably we have the best coverage. So here in the rest frame UV, we're looking in the near infrared. And so this is where optical and near infrared broadband surveys really come in. And we can really crucially use these to identify galaxies via the Lyman alpha break. And so this is using facilities like Hubble and Vista, and in the future Webb. So from this UV photometry, we're not only able to detect high redshift galaxies, but also probe the unobscured star formation, morphology and structure, roughly the ionizing photon production, dust attenuation if we believe the beta diagnostic, and also clustering if we've got large areas. Okay, so just from the UV photometry alone, we can actually start learning quite a lot about the populations of galaxies at very high redshift. We also have some limited rest frame UV spectroscopy. So for example, from the VLT. And so this provides things like accurate redshifts. We can get the IgM ionization fraction from Lyman alpha. And we can also, and this is quite tentative at the moment, but probe the ISM via some of the UV lines like helium-2 and carbon-3. And again, this is actually where Webb will really shine in the future with its exquisite spectroscopic capability, pushing all the way at least to 5 microns, but even further for the brighter sources with MIRI. We've also had some limited rest frame optical photometry, largely from Spitzer. So this has provided us kind of estimates of the stellar masses, constraints on the nebula emission, so actually showing us that these galaxies, as expected, have quite a lot of nebula emission, and providing some constraints on the star formation histories and the ages by looking, for example, at the Balmer break. Okay, but Spitzer is a relatively small telescope, and this is really where Webb is going to again shine, observing the rest frame optical here. And then as we move into the mid and far infrared, we're able to probe the obscured star formation. So together with the UV, it gives us our total picture of star formation. We can get gas masses, dust masses, dynamics. Been a huge amount of excellent work done in this over the last few years, and redshifts, where maybe if we have galaxies which don't have strong Lyman alpha, we can use C+ to actually measure the redshifts. So some of this work has been done by single dish experiments like Scuba2 and Herschel. They've been more useful actually pinpointing some of these bright sources, but a lot of the detailed work has been done by ALMA over the last few years, and there's a huge amount of science in there. So we can also think about observations in a different way. So instead of just looking at the wavelength, we can think about what variations in area and depth have told us. So in this little diagram here, we have the area of a few surveys compared to the depth. And so I've highlighted a couple of the ground-based survey, which are probing up to around 10 square degrees. And obviously there are things over here which are probing hundreds or thousands of square degrees. And then down to many of the famous Hubble surveys like the Hubble Ultra Deep Field and Candles. And so we could kind of classify these as things over here off my diagram are very wide and shallow, and they're mostly the AGN. And then we have the kind of intermediate areas like Rebecca was talking about, where we've got this overlap between the AGN and the galaxy populations. And then we have the predominantly Hubble surveys where we're probing narrow and deep regions, mostly probing just star formation in these galaxies. Okay, so we're able to combine surveys across a huge number of scales in terms of depth and area here. Also worth noting that with the lensed fields, we can push even further, although to very, very small areas. So using things like the frontier fields, we can push down to true apparent magnitudes, so unlensed apparent magnitudes of 31 or even 32, potentially in some areas. And so we can take all of this information and we can put it together, and we can do things like measuring what I think are really exquisite luminosity functions now, covering a huge range. So for example, we have, say, Vista over here, the Hubble blank fields here, and the lensing fields here. So observationally, we've been able to observe galaxies over a huge range of scales, so a huge range of luminosities, by doing this very nice wedding cake type strategy. Okay, it's actually more of an incidental wedding cake type strategy. And then with follow-up facilities like the VLT, like ALMA, we've been able to learn more about the individual properties of galaxies. And so if we want to summarize things at high redshift in terms of galaxies, we've now identified more than 1,000 galaxies above redshift 6, with the first constraint to the luminosity function all the way up to about redshift 10. And we have plausible, though bright, candidates even at a redshift 11 now. So this contrasts with where we were around 2009, 2010, prior to Wide Field Camera 3, where above redshift 6, we were talking about samples of a few tens at most. Okay, so the field has really been transformed by Hubble and by Vista over this time. And so we could reevaluate our questions and we could see what type of progress we've made. So we could consider, well, what have we learned about the first stars? I would argue that we don't have much progress here so far, just because actually distinguishing the first stars from the later stars is actually very difficult. What have we learned about supermassive black holes? Well, we know we can make very massive black holes above redshift 7. What about reionisation? This is tricky, but all the evidence points to this being consistently driven solely by star formation with no need for exotic physics and maybe no need for a large AGN contribution. That doesn't mean there isn't some AGN contribution. AGN should make a contribution, but it doesn't look like it's going to be the majority. What about the early enrichment of the universe? Well, we've had things like Herschel and ALMA have shown us that we do have very dusty galaxies, even as far as redshift 8, potentially 9. And what about galaxies being quenched? There are some indications of galaxies with declining or suppressed star formation, even above redshift 6. Okay, so there's lots that we've learned, but there are still many gaps. In terms of the observational future, we're going to be transformed from this to this in the next few years. So obviously Webb, followed by Euclid, and then Roman in a few years. And then after that, we'll destroy my diagram again with the ELT and the other ELTs as well. But this is really the domain of Emma's talk, who's going to be talking later this afternoon. So I'm going to defer any discussion there to Emma later. This wasn't originally my brief from Alyssa, but I wanted to mention some simulations of these galaxies, just because my own career pathway has moved me from the observations and into the theory more recently. So I just wanted to highlight some ideas here. So I would always say that in isolation, observations alone do not provide our complete understanding of the processes responsible for galaxy formation. So we need a model or theory. Now, there is a huge range of different galaxy formation models out there, and I'll try and summarize some of them. But there's generally this trade-off between the complexity, the realism, and the range of predicted properties, and the volumes or masses or redshifts that we can probe with these. Now, I think this early part of the universe's history is quite special because it is so early. It means we can actually do the highest resolution simulations of galaxies. We can include more physics, which might be too computationally expensive to extend all the way down to redshift 0. So that really gives us this richness in the amount of modeling that's available to us. So at one end of the scale, we have things like the empirical models, which assign observational properties directly to dark matter halos using often simple prescriptions, which are often empirically motivated. So the kind of leading work in this area are, for example, Charlotte Mason's work in 2015, I think Christina Williams' work, and several papers by Beruzzi over the years, including the more recent Universe Machine update. So these models and the DM-only simulations that they're often built on are very fast to run. This is really, really convenient for many things, particularly if you want to run large volumes, they're really useful. But they don't explicitly implement many of the physical processes from first principles. And so they're not going to be able to predict things like sizes and morphologies other than in an empirical sense. They may also fail to model some stochastic processes like mergers, which we might miss out on. But again, all of these models are useful in their own right. It isn't to say that one model is better than another. Thanks, Alyssa. As we move into complexity, we have things like the SAMs, which go a little bit further in that they take dark matter merge trees, associate them with baryons, and then do some more physical modeling here. And again, there's loads and loads of SAMs in the literature, including several SAMs which are really focused on the very high redshift universe. So in particular, the Young et al. Papers of the last few years, and the work of Pratikdayal and her group. Okay, but also Galform and L Galaxies have also done some work as well. Again, these are much faster than more complicated models, but they're a little bit better than the more empirically based models because they do try and do things from first principles. They do miss some spatially resolved information, and they do miss some of the wider interaction. The next step is really the hydrodynamical simulations, and these simultaneously try and solve the relevant equations of gravity, hydrodynamics, and thermodynamics. So they're trying to do everything in one go, but it's worth remembering that many of these do incorporate a lot of subgrid physics as well, so physics below the resolution limit of the simulation. Okay, but these are responsible for lots of these nice videos like this. Now, while these are much more expensive than SAMs, we now, over the last 5 years, been able to simulate cosmological volumes all the way down to low redshift, or even much larger volumes just limited to high redshift. So we can make diagrams like this, showing the range of kind of resolution, where these things are higher resolution over here, these things are higher volume up here, showing that we have simulations which are, again, just covering this entire range. I'm going to skip over a couple of slides, my shameless advertising bit, just because I'm running out of time. And just what's somewhat unique about the very high redshift universe is because the universe is still relatively young, we can also do more complicated modeling, for example, including self-consistently the radiation field, so with radiation hydrodynamics. Now, this is really crucial for doing things like tracking reionization, but it also appears to be really important for actually accurately modeling the lowest mass halos and therefore the early star formation accurately. But these are much more computationally expensive. This results in lower resolution and smaller boxes. Okay, and again, there are some examples here. This isn't hugely complete, but things like Coda 2, Renaissance, and Sphinx over the past few years. So that was my very, very broad general overview, just to throw some of the ideas out there. Just before Alyssa takes me away, I just want to advertise something that I hope many people are aware of. This is a program called Sazerac that myself and Steve Finkelstein at Texas developed. So this was a virtual conference that we established in response to COVID-19. And it's something which we think is going to continue. So we began with a 4-day summer meeting last year, which gave us about 500 registrations. And we've been having all of these spin-off meetings since. We also plan to do more meetings. So I think virtual conferences are here to stay. So virtual conferences are both more inclusive and they reduce the environmental impact of astronomy. So where we can, we should be doing some of these. I'd just like to just end on this advertisement for the next of these Sazerac SIPs, which is actually, it's next week, isn't it? Yep, so this is CIDR. They're called ISM during the epoch of reionization. The only thing I did with this is actually think of the acronym because that is my key skill. And I just end there. And again, thank Alyssa and the rest of the organizers for inviting me to talk.
Thank you very much, Steve. Sorry about the lone clapping. It must be awful.
I get it from my students. It's fine.
Okay, so yeah, as a side note, I want to thank Steve and the Sazerac people for being very helpful in promoting this meeting as well. That's been very much appreciated. Okay, so put your questions to Steve now. At the moment, we only have mine. So do I get to ask mine?
Go for it.
What are you most excited about doing next, Steve?
I mean, it's got to be web, right? But my excitement will be moderated depending whether the programs I proposed for get accepted or not.
Right.
If I'm left with no programs, then I might just give up and just become a theorist full time.
And utilize all of the wonderful GTO data, I'm sure.
Well, a lot of that GTO data is proprietary. I mean, yeah. There'll be a huge amount of proprietary data which I'll try and use. But yeah, I mean, web. I think, to be honest, though, I'm really looking forward to Roman. I know it's further down the line, but Roman's going to give us tens of thousands, hundreds of thousands of galaxies in this epoch. So it is going to be really transformative. We're not going to have the really great multi-wavelength follow-up from Webb, unless they do overlap. So that's a bit of a shame, but just in terms of raw statistics of galaxies and using them to constrain the models is what I think is really good.
Okay, excellent. Right. Someone else can jump in if they want to, but otherwise I suggest we now move towards our brief poster session. Okay, so people with posters, first of all, thank you very much for sending us the posters. And I hope that you are able to unmute yourselves one by one. The plan is that Maxime will be showing the PDF that's compiled each of your posters. Apologies in advance if I get something wrong here, because we didn't quite have time to check through everybody and their affiliations beforehand.
The poster should be correctly displayed now.
Yeah, okay, that's working for me. And do we have Denny Bergerella?
Yes, I'm here.
Hello. Okay, so
I
over
can see
to
very
you
well.
for 1 minute.
Okay, this slide is about dust. Oh, good morning first. This slide is about dust and its evolution in the early universe. You can see the details in the 3 papers. In slide 1 and 2, purple and blue, the redshift is used as a spectrograph to sample the dust emission of LBJs from redshift 5 to 10. Right now, I am adding the alpine sample to this sample. In slide 3 and 4, green and yellow, we see a time or specific SFR sequence. We have theoretically modeled this evolution from the right, where a galaxy builds their first dust rain from supernovae, to the center, where they reach a maximum permitting their detection, and to the left, where dust is mostly removed in the AGN by strong outflows. This same sequence might be seen in the IRX versus beta diagram. Slide 5 and 6, arranged in red, is about the far UV dust attenuation versus stellar relation. When integrating this relation over the redshift, we absolutely need 2 things. First, an evolution of the law with redshift, and second, a non-zero apparent average dust attenuation at low stellar mass. Note that I said apparent. Various explanations can be explored: a more bursty nature of the star formation, a more clumpy geometry of the star formation regions, a modification of the dust to metal ratio with metallicity, or simply that dust is building very fast in low mass galaxies. Thank you.
Thank you. Okay. Oh, right. Thank you very much, Vinny. Okay, so now on to Mattis Reitbach.
Hi. Most galaxies in the epoch of reionization are neither quasar hosts nor massive, rather they are metal-poor dwarfs, which makes them extremely challenging to study. But we can still get crucial insights from their analogues at intermediate redshifts. And so what we tried to do here was to look at the molecular gas content of a redshift 2 strong valence dwarf, as you can see up right, using one of the DP Zalma Band 9 observations to date targeting the C2 emission line. And surprisingly, instead of getting a super bright line detection, we had to take a Rorschach test. And we only find 3 to 4 sigma tentative detection, which places the C2 emission orders of magnitude below locally calibrated relations, but in good agreement with models that predict that C2 will go down with metallicity. And this has interesting implication for both the underlying ISM physics and detectability of these galaxies in the EOR. And that's it.
Fantastic, thank you. Okay, on to John Weaver.
All right, hi everyone, if you can hear me.
Yep.
I just want to make a brief pitch for the imminent release of the Cosmos 2020 Galaxy Catalog, which contains about 1 million galaxies from a near-infrared selected combined image from ultra-deep near-infrared and optical data. You can see on the right-hand side how we've improved from the gray bars from 2015, so that's really great for our photometric redshifts. We perform our photometry with 2 methods, an aperture-based source extractor approach and a model fitting approach with the tractor from Dustin Lang et al. Over 39 bands, we achieve photometric redshift accuracy on the bright end, less than 1% on the sigma NMAD and around 4% on the faint end, which translates to the high redshift universe as well. We generate these photo-Zs and physical parameters with two codes, meaning that we have 4 sets of photometric redshifts and stellar masses, which means we can check our systematics when we start to go and explore the high redshift universe with more robustness than we've ever been able to do before over 2 square degrees. So watch out for this on archive. And once it's released, please have a look at the catalog and use it for all the wonderful science that we can get out of it. Thank you.
Fantastic. Thank you, John. Okay, do we have, is it Lena or Lena? Lenz?
Yeah, Lena, yeah. Mm-hmm.
Lena. Hi, Lena. Okay, over to you.
Hi. Yeah, so thank you. We developed automated methods to find high redshift quasars in Euclidean LSST data, specifically redshift above 6. And so we have two main approaches. So one of them is this chi-squared approach, where we model a quasar to be a point source that is stationary throughout all passbands, and that also follows a quasar SED. And we do model checking at the pixel level. So if you look at these two rows of the postage stamps, for example, the first row is a quasar, and the second row would be our residual, where we use a Moffat point spread function to reconstruct the photometry. And as you can see, this is all just noise, which is great. And then we have another approach which is a Bayesian model comparison, which is based on color information. And this is to get rid of the contaminants. And those two go well together. So if you look at the scatter plot, you can have a high quasar probability just based on the photometry alone. But the source might not be a point source, or there might be some data issues. So then you will be at the top right corner. But on the other hand, maybe your source does look like a quasar, but actually it's much more likely that it's a contaminant. And then it will be on the left bottom corner. I should also note that this is based on visual inspection, the labels on this plot. Yeah, thank you.
Thank you. Okay, over to Jan-Torge Schindler.
Hi, I'm a postdoc at the Max Planck Institute for Astronomy, and I work in the groups of Fabian Walter and Eduardo Bañados, and I would like to introduce you to the X-shooter AMA sample of Reionisation era quasars, which was published last fall. So the sample is comprised of homogeneously reduced and analyzed X-shooter near-infrared spectroscopy of 38 quasars above redshift 6, which have complementary ALMA data available. We have analyzed carbon-4 and magnesium-2 velocity shifts with respect to each other and the carbon-2 line from the ALMA observations. And we find that strong carbon-4 broadline region winds are more common above redshift 6 than in low redshift quasars. Furthermore, the magnesium-2 line with respect to carbon-2 is on average actually blue shifted with a median of 390 kilometers per second, and the shift correlates with the carbon-4 carbon-2 velocity shift, indicating a common physical origin. We also analyzed the broadline region iron enrichment by measuring the iron-2 of a magnesium-2 flux ratio, and we do not find it evolving even at the highest redshift, suggesting rapid iron enrichment to take place above redshift 7. If you're interested in this work, please check out our paper, which I have linked to the poster on the Slack channel. Thank you.
Thanks, JT. Oh, perfect timing. Very good. Okay, so over to Thomas Schulzinski. Are you here, Thomas?
Says he's unable to unmute.
Okay. Thomas. Oh, yep, sorry, that didn't work for some reason. Okay. Okay, Thomas, you should be able to unmute now. No? Okay, I'm going to move you up to panelist. Let's see if that helps. Okay, shall we move on to the next person and come back to Thomas?
Sure.
Okay, so final or penultimate poster actually now will be the work of Teresita Suarez Noguez, presented by Avery Maxime.
Yes, thank you. Yes, this was predominantly Teresita's work. She's on maternity leave, so she's not been able to present it herself. What we did is concentrate on the CGM, on low metallicity absorption systems found in high redshift quasars during the epoch or near the epoch of reionization to see what we could learn about the properties of the galaxies and possibly about the radiation field. What we did is we modeled the clouds as pressure confined, presumably in the halos of the galaxies, and used cloudy to do the radiative transfer. Moving from left to right, we rolled the clouds into cylinders, and the idea of doing that was to be able to probe lines of sight that don't pass through the center of the clouds, as would be conventional with cloudy models. When we do that in the second panel, we see we get a large range of possible values. And we find that in terms of the abundances, the metals correspond to metallicities between metal abundances between solar and starburst abundances. We've done this now for a wide range of data that's rapidly arising from high redshift quasars for these low metal systems. We do find that it's important, if we look at the third panel, to resolve these systems. If we look at one of the smaller red points, if that's a combined system, if the system is separated, this data from Pudel et al., it separates into the two golden crosses, and it actually changes the story. So it's quite important. Instead of seeing a system near solar abundance, we see one near solar and one near starburst. We see in both panels that in several cases, the abundances are below what's expected for the silicon to oxygen ratio for the abundances. And that's an indication, in fact, of depletion onto dust. So it's showing that these systems seem to have an evolved ISM. And lastly, we looked at a system, rather than using the conventional Hart and Vidal UV background, we looked at Cookvine's late reionization model and found that the predictions actually show us clouds that are almost entirely neutral. And so we would really mostly expect only abundances from an indication of the abundances, whether it's solar or starburst or something in between. But the data suggests maybe a wider spread than that. And if we use the Hart and Vidal spectrum, we would get a wider spread. So this is perhaps not favoring the late reionization scenario, although the data are still noisy. With more quasars at high redshift, we hope that in the future we'll be able to make these constraints more sharp. All right, thank you.
Thank you, that was wonderful. Okay, so Thomas has rejoined us.
Yeah, sorry for the technical issues.
Okay.
Hi, I'm Tomáš Schulzinski, PhD student at the University of Nottingham. We explored the 21 centimeter forest in these novel laden patchy reionization models using the Sherwood Relics simulation suite. So in these models, you can find large islands of neutral hydrogen at redshifts as low as 6. This means that there is a possibility of detecting the 21 centimeter forest at such low redshifts in this, quasar or radio loud spectra, radio loud sources spectra. However, what we find is that this signal 21 centimeter forest is quite sensitive to the X-ray background heating. As you can see in the middle plot in this synthetic spectra, as you increase the X-ray background efficiency, you suppress the signal. On the other hand, we suggest a way of constraining this X-ray background by looking at the redshift interval needed to detect a single 21 centimeter forest absorption feature. And right now we are at this stage of preparing the paper about this, so stay tuned. Thank you.
Fantastic, thank you. Okay, so we've reached the end of the morning session, which is pretty good. Okay, excellent. Everybody's here. Hi. And we tested this morning, so hopefully all is well there. Right, so I can introduce the first speaker, yes? Have I forgotten something else?
No, I think it's
okay. So let's go ahead with the rest of the contributed talks. Again, we're going to be doing the 12-minute.
No. We could start, I think. So we'll start with Mauro Stefanon, please.
Yeah. Okay. Good afternoon, everybody. My name is Mauro Stefanon. I'm postdoc in Leiden. And well, first of all, thanks the organizer for giving me the opportunity of talking about some of my work. Today, I'm going to talk about some of our most recent results on the efficiency on the assembly of the stellar mass at early cosmic epochs. Why is not working this? Okay. So in the last decade, the synergy between the major observatories has allowed us to uncover a variety of stellar population in the early universe. And an exciting new result has been the discovery of very, very massive systems at high redshift. And these systems are raising questions about our understanding of how efficient was the stellar mass assembly at early epochs. So one way to probe this, to try to answer this question, is to compare the accretion of the dark matter halo to the assembly of stellar mass. So how can we actually constrain from an observational point of view the stellar masses assembly? Here I'm just sketching and listing some of the ways that we have to measure, to estimate, or to constrain the stellar masses. They refer to a variety of different physical processes and also time dependencies and time scales. Okay. In this talk, I will concentrate on two in particular. So one is direct measurements of stellar masses at different epochs from studies of large numbers of sources. And on the other side, I will also present results on the evolution of the specific star formation rates. These two methods, and actually also other methods, rely on one fundamental ingredient, which is they need very deep, very high signal to noise, preferably very high signal to noise, data at rest frame optical. And at the moment, before JWST, we can only probe the rest frame optical at high redshift through Spitzer IRAC observations. So let me just briefly introduce GRADES, the Goods Reionization Era Wide Area Treasury from Spitzer. This is an IRAC legacy program led by Ivo Labbe, and we are really going to publicly release the data, the mosaics, very soon, which substantially increase the depth available in the IRAC 3.6 and 4.5 micron over the two goods fields. So just to give a very rough idea of the kind of improvement, the GRADES provides extends by a factor of 5, more or less, the ultra deep coverage that is now available only on the IUDF small region. So it's but it's not just that small area that it is increased. The coverage, the gain in sensitivity is spread over the full fields of the two fields. So far, even with the deepest data from IRAC, we could probe the rest frame optical of galaxies at high redshift only for those galaxies which are let's say, brighter than L star, so very relatively bright and massive galaxies. But thanks to GRADES, we can dig deeper, right? So here I'm showing you in these 4 panels are the results from stacking approximately 100 galaxies, Lyman break galaxies that we identified at redshift 8. And for which we have very deep IRAC data from GRADES. And we can see that there are two main features for this stacked spectra. One is a blue H-3.6 color. Okay, so H here, it's comes from HST, and at this redshift, H probes the rest frame UV. And the 3.6 micron data instead probes the rest frame optical. So H-3.6 gives us sort of proxy for H. There is quite a distance, I know, in wavelength, but this is the best we can do right now. And a blue H-3.6 suggests very young stellar ages. The second important feature is a red 3.6 minus 4.5. So 3.6 is this band here, and 4.5 micron is this band here. You can see already here that we have like 0.5 or even more magnitude color, right? And this is this can be interpreted as the result of very strong emission lines which are entering the 4.5 band. And at this redshift 8, we have O3 and H beta, which are very strong. And this color, the color that we find, that we measure, imply equivalent width of about 1,000 angstrom. So these are very extreme emission lines. And again, such extreme emission lines point towards very young ages. But we can go a step further, so we can combine this information and try to measure the specific star formation rate. Right? As you can see, this is presenting in these two panels, segregated by more or less stellar mass or luminosity. And the interesting result here is that our measurements, and also combined with measurements from previous studies and at lower redshift, and also, well, consistent also with the higher redshift, indicates that the specific star formation rate is evolving at the same way as the specific accretion rate of the dark matter halo. So this again indicates, is suggesting that there is no enhancement in the efficiency of the star formation at this redshift. This is true, I would say, for the mass, or for the higher half mass of our sample. For the lower half mass, we can see that there might be some weak dependence on stellar mass. But this is, again, so as you can see here, the error bars are quite large, and it's very difficult to say anything. So in the second part of the talk, I will present a different perspective on how we could probe the evolution of the efficiency of star formation. And we did this by studying the evolution of the stellar mass function of galaxies, of field galaxies, in the first giga-year, right, of cosmic history. And we base our study on the so far largest sample that we have access to from the 5 Candace fields. So this gives us about 1,000 galaxies at redshift 6 and above, and over an area that is approximately 3 times larger than previous studies. And of course, again, also in this case, we have the Goods North and Goods South fields, for which we have the great data, which allow us to go quite deep with in our stellar mass estimates, stellar mass completeness. This is our measurements of the stellar mass in 5 redshift bins, from redshift 6 to redshift 10. And our measurements are this blue field blue circle here. There is, in general, agreement with the previous estimates. There are some systematics, especially at redshift 9, but this means 2 things. One, that we don't know, there are still many things that we don't understand about stellar mass at this high redshift. And the second, believe me, it's extremely difficult. It's extremely challenging to compute stellar masses at redshift 9, in particular, from photometrically selected Lyman break galaxies. So there is a lot of caveats here, right? But I think these results are quite encouraging. And indeed, we can, again, go one step further and compute the stellar mass density. So the amount of stellar mass in the universe. And this is shown here with the red points here. And the interesting thing again here is that the orange region, I'm not sure if you can see it, but there is an orange region here, is the, evolution of the halo mass density from abundance matching, right? And which has been rescaled by a constant factor of 100. So the halo mass density would be actually right here, up here, because we have much more halo mass than stellar mass. But if we rescale it by a factor 100, independent on the redshift, we find that its evolution, or the evolution of the stellar mass density, follows the evolution of the halo mass density. And again, this suggests that there is no change or no drastic change in the efficiency of star formation, at least in the first giga-year of cosmic time. But the stellar mass density depends, the number that we derive depends on the low mass and on the abundance, sorry, of the lowest mass galaxies in our sample. We can ask ourselves if there is any dependence on the stellar mass, right, of the stellar to halo mass ratio. And this is shown here, our result. So again, this comes from abundance matching. So I was matching the abundance of from our stellar mass functions to the abundance of the dark matter halo from halo mass functions. And it is quite, I would say, exciting and surprising also that we find a very clean and narrow correlation between the stellar mass and the halo mass across all the 5 redshift beams that we considered. And again, so this is again another confirmation that, or another help that we probably don't see much evolution in the efficiency of star formation. And honestly, I lost track of my time. I think I'm overdone. So here are my conclusions, and I'll take any questions.
Fantastic. Thank you very much, Mauro. And that's on me for not giving you the 2-minute warning. So, okay. Right. There's a couple of questions, and David is on questions for this session. So.
Sure. Okay. If we go with sort of the first one that came in.
Yeah.
That is, the question is, how do you know that these objects are star-forming galaxies and not AGNs, the objects greater than redshift 6?
Yeah, that's a good question. Well, so Rebecca this morning showed that one of the criteria that she used was to look at the HST ACS images, and from there, for the very, very massive ones, she could see that those have those are like point source like, right? So we inspected this and excluded those which were point sources, and then from the, where is it? Where is here? So from the SED, I think that if we had AGN, I would have expected to see a radar starting to already in the optical. You usually start to see radar SEDs here, which go up and up, and here instead we see very blue things, and yeah.
Okay. Thanks very much, everyone. So there's a lot of questions coming in. So if we could continue that in the Slack, then that would be really good. Okay, so moving on to talk number 2. Okay, so with that, let's move on to the next speaker, who is Viola Gelli. And she's going to talk about high redshift Lyman break galaxies with JWST.
Yes, I will share my screen. So can you see it?
Yeah, excellent.
Okay.
Okay, great.
So good afternoon, everyone. I am Viola Gelli, and I am a PhD student at the second year of the University of Florence. And today I'm going to talk about satellite dwarf galaxies of high redshift Lyman break galaxies. So first of all, why dwarf galaxies? We are interested in dwarf galaxies because we know that they are particularly important, especially in the high redshift universe, because they are the first galaxies to form in the lambda CDM context. And also they are the building blocks for the formation of more massive systems. We know that JWST will provide us a great opportunity to observe these galaxies directly during the epoch of reionization for the first time. So what we asked ourselves was, where can we find these dwarf galaxies within the high redshift universe, within the complex cosmic web, let's say? What we know is that here in the local group, we have many dwarf galaxies that behave as satellites of more massive systems like our own Milky Way. So what we expect is actually a similar behavior also at high redshift, where we expect to have many dwarf satellite galaxies surrounding massive systems there, like typical Lyman break galaxies. So to study dwarf galaxies in this specific context, we used high-resolution cosmological simulation. In particular, this one was developed by Pallottini in 2017. And this simulation reproduces the observed properties of a typical Lyman break galaxy at redshift 6. So here I put a stellar map of the stellar map density of the galaxy. Here you can see the disk of the LBG, which is called Althea. But what we do see around the Lyman break galaxy are also all these stellar overdensities, which are indeed the satellite dwarf galaxies that we expected. They cover a wide range of masses, going from 10 to the 6 to 10 to the 9 solar masses, and they are all living inside the dark matter halo of the main LBG. Actually, 5 of these objects are galaxy in the sense that they have their own dark matter subhalo. But one of them, the smaller one, it do not present dark matter or neither gas, so it's more similar to some kind of protoglobular cluster. But what we want to understand about these objects is which mechanisms drive their evolution. And to do this, we studied the star formation and metal enrichment histories, and their properties from this point of view can be divided mainly into categories. So, and this is based mainly on their mass, depending on their mass. Let's start with the case of low mass satellites. Here I show the age metallicity relation of the star composing a typical low mass satellite, along with its star formation history and its metallicity distribution function at redshift 6. What we do see is that a low mass satellite form all of its stars in 2 short bursts of star formation. And during these bursts of star formation, the metallicity of the stars formed increases in time, reaching supersolar values in the end. What I want you to notice is this first interruption of star formation, and more importantly, the fact that after the second burst, the satellite is completely quenched. And this is caused by supernovae feedback. So the internal feedback by supernovae is the main responsible for the complete quenching of these objects. On the other hand, we have the case of high mass satellites. They are much more complex. Their star formation histories, for instance, are much longer, lasting up to 500 million of years. And their metal enrichment histories are even more complex, characterized by all of these vertical trends, meaning that stars with lower metallicities are formed. So what do they mean? they correspond to merger events happening in these satellites. And this means that it is merger events that can fuel star formation in this system, somehow counteracting the effect of supernovae, which would have quenched it, and allow the system to keep on forming stars for longer times. So to have a more general idea of how the properties of these satellites depend on their mass, here I plot indeed some of their properties for each satellite and also for the LBG Althea as a function of their halo or subhalo mass. What we see is that both the time of the first star formation event happening in the satellite and also the initial metallicity of stars show a decreasing trend with the mass, meaning that lower massive systems form later in an environment that had already been pre-enriched by the star formation happening in the LBG itself and its progenitors. While on the other hand, higher massive satellites form previously in an environment that was somehow still pristine and unpolluted. Other quantities like the length of the star formation activity and the mean metallicity of stars show instead an increasing trend with the halo mass. But actually, we may notice that the mean metallicity of stars for all of our satellites, it's around solar values for the lower masses and the higher masses as well. But however, if we go and check the amount of metal poor stars inside each of these objects, we obtain that the trend of the fraction of metal poor stars decreases with the mass, meaning that lower massive systems are indeed in proportion more metal poor. We have now, let's say, a global picture of the properties and evolution of how these satellites behave in these dense environments of the cosmic web. And for instance, this kind of behavior is peculiar of these dense environments. But what we want to understand now is if we will be able to detect them, for instance, with JWST. And in particular, we want to understand if we could observe their stellar emission. So what we did with this aim in mind is modeling the stellar emission. And here I show you the resulting spectra at Redshift 6. So this is the range that the near-infrared camera on board of JWST will observe. And these are indeed the sensitivity of the various filters to give us an idea, let's say, of what we will be able to detect effectively. For instance, if you remember the protoglobular cluster that I mentioned at the beginning, it will be not detectable for sure because its flux will be too low. But the other 5 galaxies that I show, as well as Althea, of course, which is the main LBG, all of them will be, in general, mostly above the limits, meaning that they will indeed be observable. But to have a preliminary idea of what effectively the NIRCam instrument will observe, I produced these mock images at Redshift 6 in 2 different filters for different time of observation and signal to noises. What we obtain is that the satellites will be observable and also resolved in some cases. And also, for instance, we can notice that in this filter, all of them will appear in already just 3 hours of observation. So to conclude, what I showed you was that in a simulation of a typical Lyman break galaxy at Redshift 6, we found 5 satellite dwarf galaxies and also 1 protoglobular cluster. We demonstrated that supernova feedback in these environments is still the key mechanism responsible for quenching low mass systems. On the other hand, merger can counteract its effect, fueling star formation and keeping it going for longer times, so creating higher massive systems. Finally, we saw that with JWST, we will effectively be able to observe these satellite dwarf galaxies. And moreover, we know that with NIRCam, already in the first guaranteed time observation surveys, we will expect to observe tens of Lyman break galaxies like the one that in our simulated one. So as a consequence, it will come that for free, we will have parallel observations of hundreds of satellite dwarf galaxies. That's it. Thank you. If you have any questions, I also leave it here, my email. Okay.
Thank you very much, Viola. Okay, any questions?
Yes, there's a few that are popping up on the Slack now. I'll just pick one. Do your simulated spectra include the effects of dust and nebular gas self-consistently?
Yes, it does. So you can also see here, it's a bit faint, but the dashed line that you can see are the intrinsic stellar spectra. Then we added the contribution of dust. So we see that somehow its effect is, of course, to lower the flux. But the thing is that at this stage, for instance, which is at Redshift 6, these satellite galaxies, which are very low massive, own not a great amount of gas and dust. So in this phase, when they are passive and not forming stars, the contribution of dust is taken into account, of course, in our simulation, but we see that it's not so important, let's say, because they are completely dark matter and star dominated. I hope this answers the question.
Yeah, okay.
Do we have time for others? There are some others.
Yeah, I can see that there's lots of questions coming. Maybe just very quick one.
Okay, very quickly. Do you expect the presence of an AGN in the central galaxy to affect the satellite dwarfs and their star formation history?
Let's say that it's not been taken into account in this simulation, because it's a simulation of typical observed Lyman break galaxies in which an AGN has not been observed. So it was not the aim of simulating the effect on AGN. Moreover, of course, the simulation aims to reproduce observational properties and succeeds, you can see in the paper that I mentioned of Pallottini, succeeds in reproducing important observational properties like the C+ emission and also the Schmidt-Kennicat relation. And so many of these objects have been observed in literature, and more of these, also without an AGN, are expected to be observed with JWST. So this was the kind of typical environment that we wanted to investigate.
Okay, excellent. Thank you very much. So final talk of the Galaxy session will be Michele Janolfi. Oh, there he is. Phew, your name disappeared. I was worried.
Can you see me? Can you see my slides?
Can see your slides. Yeah, everything's brilliant. Okay, right. So away you go.
So thanks, Alyssa. And yeah, I just want to show you some of the research, the recent research I've been doing on some of the mechanisms of the galaxy baryon cycle and high redshift, like galactic feedback, gas stripping, and CGM metal enrichment. And let me start from outflows that we know models invoked since years to explain many observables. And one of the best techniques to observe outflows is to look at the blue shifts of the metal absorption lines with respect to the systemic redshift. And this has been done in the local universe and in the medium redshift, but a higher redshift, it's actually more difficult because of increasingly weaker metal absorption features in the spectra, and also, more importantly, large uncertainties on the systemic redshift itself, which most of the time rely on Lyman alpha, which is not accurate indeed for the systemic redshift. Another way here could be using the emission lines, looking at the broad wings at the high velocity tails of the spectra, like people have been doing that with the C2 in the X-ray far infrared, both in ULIX in the local universe with Herschel and also with quasars in the high redshift universe. But for normal galaxies, like main sequence galaxies, the bulk of the population, and for star formation driven half-flows, this is more difficult because these features are fainter. So either we go super deep or we stack, but in that case, we need a lot of galaxies. So here what we need is statistics or systemic redshift, as I said, and here Alpine can help a lot. Alpine is a recent ALMA large program that observed C2 and DAS for more than 100 normal galaxies at redshift between 4 and 6. Here you can see the flux maps and the stamps and the kinematics map produced by Gary Jones, Cambridge. And among the many things that the team has done, which I don't have time to go through, unfortunately, what we did was to stack the C2 spectra that you see here from the C2 detected galaxies. And interestingly, what we got was that galaxies with star formation rate lower than the median star formation rate of the sample, which is 25 solar masses per year, do not really show any sign of broad wings in the spectra, or at least below the sulfur brightness threshold that we have, while the high star formation galaxies, they do show in the stat spectrum, although low signal to noise feature of broad wings and the high velocity tails, so around a few hundreds of kilometers per second. So these are signatures of star formation driven half-flows, which, by the way, very recently have been found also in individual galaxies with very deep ALMA integrations. We're talking about more than 8 hours of observation time, and they also find in individual galaxy, which I find really interesting, this outflowing gas traced by C2, kind of corroborating what models predict, that C2 is indeed supposed to catch most of the outflows energetics because of its capability of tracing multiple phases of the gas. So we wondered how efficient are these outflows, and so that's why we measured the mass outflow rate and compare it with the star formation rate. And what we found is that the mass outflow rate is actually comparable with the star formation rate, leading to a mass loading factor of about 1, which means that indeed star formation feedback is not really dominant in a rapid quenching of galaxies at redshift higher than 4, and you still need some other mechanism like AGN feedback or environmental effects to prevent further accretion and quench galaxies. So as I said, we can also use C2 as a systemic redshift tracer and then go back to the rest frame of these spectra and check for the absorption lines. But the problem is that, again, these spectra are quite faint. Lambda alpha is bright, absorption lines are faint. So again, stacking can help. And you can see here that after aligning the galaxies with respect to the systemic redshift traced by C2, the combined spectrum is quite high signal to noise. And we can now focus on the metal absorption line. And here, an interesting thing I think to do, this is something that I'm doing, the paper is in prep right now, is to bin the sample in star formation. And what happens is indeed, if we create a bin, which is the best compromise in terms of signal to noise per bin, what we find is that the more star forming the galaxies are, and the larger is the offset. It's like the blue shift of the silicon 2, for instance, which is the most prominent line with respect to the systemic redshift. And you can see that better here, I guess, where what we find is indeed the positive trend of the outflow velocity with the star formation rate. But interestingly, what we find is that the bulk of the outflowing gas is never going at velocities higher than 500 kilometers per second, at least in our galaxies. And this is interesting because if we then go back to the ALMA data cube and we combine them to check the morphology of the gas, what we find is that the high star formation galaxies, which are the one who also show signature of outflows, they do show C2 extended emission, which is more extended than the relative size of C2 size for lower star forming galaxies, and is more extended than the UV counterpart, the far infrared counterpart, and it goes up to scales of about 15 kiloparsec, and is likely tracing an envelope of metal-rich gas. So what's happening, what we believe is happening here is that these high star formation galaxies, which both show signatures of outflows and C2 halos, we think that these two observations are connected, and the explanation is that the outflow velocities are always almost lower the escape velocities of these galaxies, and so the largest fraction of the gas, outflowing gas, won't be really able to escape the dark matter halo and will be trapped in the CGM, which is what we see in these C2 halos. And by the way, this is something that has also been explored in individual galaxies recently by Seiji Fujimoto using alpine galaxies. What he's finding is that the C2 halos tend to be galaxies with highest formation rate, again, the probable powering mechanism of these outflows, and also by Rara-Kamiush, this galaxy that I showed before, showing signature of star formation driven outflows, also showing C2 halo. So again, this corroborates a possible connection between outflows and metal-rich halos, even though this is a pretty open field. So another thing that I want to talk about quickly is that outflows are not the only player here in mixing the gas on scales larger than the disk. We also found that gas stripping can play a role, and especially in a very dense environment. Here I'm showing a single case where we have a major merger between galaxy A and galaxy B here, which have a mass ratio of 1, basically, 0.92, and star formation rate of about 40 solar masses per year and 100 solar masses per year. And then there are also two satellites, C and D, which are orbiting around B. And what we find is that there is this envelope of C2, which is surrounding the merging system, and actually 50%, like half of the C2 flux is coming from regions which are not really connected to the galaxies themselves composing this merging system. And what we think is that gas stripping here is playing a role, since outflows, even assuming a conservative assumption of high mass outflow rates, and in the unlikely assumption of no reaccretion occurring, are just not able to explain this large flux on large scales. So what we think is that here the C2 extended flux is actually tracing gravitationally shocked gas due to tidal stripping, which is something similar to what has been observed in local galaxies, where C2 is indeed bridging between merging components in dense systems. I think I'm running out of time. I skipped this slide, and I will leave you with my conclusion, just to say that altogether our findings suggest that outflows, mergers, and gas exchanges with the CGM are at work in regulating the evolution of galaxies already at this very early cosmic epochs. I thank you.
There's your round of applause. Thank you very much, and very nicely timed as well. Okay, questions coming through, David?
Yes, we have a few. Let's see. Where are we? Here we are. In the UV absorption line spectroscopy, do you see any difference in the covering fractions of low ion metal lines between the galaxies, with and without the C+ halos?
No, actually, I didn't even check the subsample of galaxies with C2 halos, because, well, actually I did, but the galaxies which show C2 halos, like the individual galaxies showing C2 halos, are I think 5 or 6, and they're presented in the Fujimoto's paper. And stacking the UV spectra, you don't have enough signature noise to find the absorption line with enough significance. So what we are stacking is star formation rate. to get at least, if I remember correctly, 15 galaxies per beam.
Okay, there's one other if there's time.
Yeah,
Yes.
go for it.
Are there signs of C2 halos in the UV plane?
That's a good question. So what I did in my work was to only stack the galaxies in the image plane, the cubes in the image plane, but I was, basing upon a previous work led by Fujimoto et al., who stacked the fewer galaxies from a previous pilot sample in the UV plane, and he also found these C2 halos.
Okay, so am I on mute? Yes, I think that brings to a close the Galaxy session. Thank you very much. So at this point, I'm handing over to Maxime, who is going to chair the final session where we start looking towards the future.
Thank you very much, Alyssa, for this. We'll start the session with a review on the James Webb and other upcoming facilities from Emma Curtis-Lake from the University of Cambridge. I'll give you a 2 minutes warning, 2 minutes before the end.
Thank you. Just making sure I'm choosing the right desktop. And you see my first slide?
Yep, everything's.
Thank you. So first off, thanks so much to the organisers for the invitation to talk about such a fun topic. We just get to talk about all the amazing stuff that is coming along in really the not too distant future, right? Well, I was going to say, if you don't recognize all of these facilities just from their pictures, let me give you a quick overview in the form of a timeline. So we're all waiting with bated breath and fingers crossed for JWST. So hopefully this is going to launch this year. Currently, the launch date is Halloween. So hopefully that's not a horrible joke. And hot on its heels, we're looking at the launch of Euclid next year. So this is a really short timescale. Complementary to Euclid, we're looking at the Vera Rubin Observatory and the commencement of the 10-year legacy survey of space and time survey. So that's in 2023. And in 2023, we also have a new spectrograph to come online. It will be commissioned in first light at VLT mid-2023. And then a bit further in the future, we're looking at the really huge mirror telescopes on Earth. So we've got the ELT. This talk is a little bit European centric, so there are obviously other big telescopes with big mirrors planned, but I'm really only focusing on this one. And we've already heard some about the Nancy Grace Roman Space Telescope as well. My understanding of this one is that the funding and therefore the timescales are somewhat linked to JWST, and I couldn't find any extra information over a mid-2020s launch. So if anyone else has extra information, you should definitely put that in the Slack. And I just thought we should think about there's kind of two sides of the discovery space in front of us in this decade, and it's really going to be transformational for this field. We have the side where we're going to be finding more objects. So currently we have just a handful of Redshift 9 galaxies, right? And even less of them have spectroscopic confirmation. And then on the other side of it, we can be studying them in detail. We can be learning about them, the chemical abundances. This is so exciting. And of course, one facility that can do all of this is JWST. So let me start here at least. To give you a quick update, in autumn last year, all of the environmental testing of the whole observatory was finished. So individual components had been put through environmental testing, but at that point it was the whole thing. So you've got the mirror and the instruments and the sun shield and the bus. That's all been put together, and they wanted to put it through the stresses of launch. So they shook it up and they pummeled it with low frequency sound waves from massive speakers for the acoustic testing. And then after all that, they had to check that it was all going to unfold again and that they hadn't broken it. So this was all completed in December last year. And the final test was the unfolding and the tensioning of the sun shield, which is what you can see here. So the schedule is actually looking good. There's almost 50 days in the schedule margin available. The teams are currently working on planned sun shield patching and repairs. So this wasn't unplanned sort of, oh no, we've ripped the sun shield, but there's some reinforcements, and then they're doing some system tests in parallel. And then the next stage is going to be packing it up, and then it's got a very long journey. It's currently in California. It's got to get to Kourou, French Guiana, and it's going to get there via the Panama Canal in its very own barge, which has been made for it. So literally shipped. And from there, it can go into the Ariane 5 and be launched off into space. So I know we'll all be very excited and very, very nervous in October this year as it goes through. So I'm not going to give you a full JWST primer, just a quick reminder. In terms of finding more objects, we definitely need imaging, and we've got that from NIRCam and MIRI. But let's not forget about slitless spectroscopy, because there we're not requiring the targets beforehand. We don't know what we find. So we've got 3 of the instruments actually have slitless spectroscopy options. I don't know why I left MIRI in parenthesis there. And then on the other side of things, studying them in detail, we're going to have many more filters than what we've had. We've heard about how hard it is to get stellar masses just from the 2 Spitzer bands, the most sensitive ones that have continued working. Whereas with NIRCam, we're going to have a much larger filter set with some medium band filters, narrow band filters, and then we'll have MIRI. So MIRI is a little bit like what Spitzer has been to HST. MIRI will be to NIRCam, except with less of a sensitivity gap and more filters. So then we're probing the rest frame optical at the very highest redshifts. And then we have spectroscopy. I've already mentioned slitless spectroscopy. We have the multi-object spectroscopy from NIRSpec, the array of tiny, tiny shutters that we can open and close based on what we want to observe. And there are 2 integral field units, so spatially resolved. So we can look at NIRSpec and MIRI. They both have IFUs. So I'm going to take you through some of the already planned programs, but I would like to orientate you on the sky as to what we already have in terms of Hubble data and ground-based data, mostly survey-based. So if we think of Hubble, one of the transformative data sets from the last few years has been candles. So taking you through the fields, we start with Good South, where the Hubble Ultra Deep Field is just a small patch of that. Go around to UDS, Cosmos, Good North, EGS. Okay. And then we also have had the Hubble Frontier Field Survey. We've just been hearing about that from Rajna and Maru. And this was using natural magnifying glasses of massive clusters to be able to probe much fainter galaxies down the luminosity function. Then wider areas to look at more bright, rarer objects. That's really been done from the ground. And Vista's been leading this. And these are a couple of plots from Rebecca Bowler's paper in 2020. So covering the UDS and Cosmos. And then in terms of some accepted programs for JWST, I'm going to start with the ERS programs. So just to remind everyone, these don't have proprietary time, and it's kind of about testing the observatory very early on. And this one here on the EGS, this one is the SEERS program. PIC Finkelstein. Steve Wilkins is also co-I, so if anyone has extra questions about that, you know he's been online, so you can ask him. So testing out lots of different parts of the instrument. We've got NIRCam deep images, NIRSpec spectroscopy, NIRCam slitless spectroscopy, and MIRI imaging. So what's pretty awesome here is the overlap of NIRSpec spectroscopy and slitless spectroscopy will give an empirical measurement of slit losses from NIRSpec, which is going to be integral to the years coming ahead. And to highlight one science case that SEERS is going to be able to address very, very quickly, right, in JWST's lifetime, this is the build-up of the highest redshift galaxies. There has been a little bit of disagreement as to whether there's this very quick evolution, and maybe we're seeing the sort of first assembly of the halos, or whether it's perhaps been a little bit flatter. And SEERS predict that they would see about 5 Redshift 10 galaxies, or 50, depending on which case it is. So already very early on in the JWST lifecycle, we're going to be addressing these problems. The second ERS program I'm going to highlight is sitting on this cluster, Abel 2744. So this is the GLASS program. This is deep spectroscopy of this cluster field. So there's nearest slitless spectroscopy. Sorry if you can hear my mouse, I can hear it scratching around. Nearest low resolution spectroscopy, near spec, high resolution spectroscopy. So this is really for the highest redshift. This is looking at Lyman alpha. This is looking at the spatial profile of Lyman alpha from nearest, and then the line profile with the higher resolution from near spec. And with that, we can probe the escape of ionizing photons within the epoch of reionization. Along with this, there's going to be very deep near-cam imaging. So these are two new deep fields, right? They're not going to coincide probably with the HST parallels, so they're not going to have such deep optical, but these are prime fields for discovery of new targets at the highest redshifts. And these will be the deepest imaging in the ERS programs. So here's two of the most relevant programs, I think. There's also templates, and that's just a couple of objects. But to highlight some of the GTO programs, there are a couple that are involving the strategy of using near-cam imaging with near-spec follow-up. So the first one here is Canucks, where we have, they're targeting 5 different clusters. I've actually added one here because it wasn't one of the frontier fields clusters. They've got nearest spectroscopy for that because it's the nearest GTO team, but also near-cam imaging with near-spec follow-up. And the other notable program doing this is the JADE survey. So this is the joint near-cam, near-spec GTO teams, and the one that I'm involved in. So this is covering the Good South and Good North. The Good South, so we have 2 different depths of near-cam imaging mosaic, and then the stuff that goes off to the side is coordinated parallels. And in Good North, we just have 1 depth of the imaging, so that's the slightly shallower. And then the blue points here are where we get near spec follow-up of near-cam targets. And then when we have the green pointings, that's coordinated parallels. So we're using what we know already from HST. So the power of combining near-cam and near-spec. First off, I've already talked about there being many more filters. So it's hard to see, there's actually a medium band one here as well. So these are the chosen filters for the JADE survey. And what you can do with these narrower filters is start to deconfuse the contamination from emission lines. So this is currently very hard to do with Spitzer, and it means that the estimates for stellar mass are much more uncertain. So we'll have much more certain stellar mass estimates, and then also we'll be able to make the selection from the rest frame optical. So where we may well be missing objects from our standard sort of high redshift criteria of looking for this Lyman break, we could be missing either very dusty or quiescent galaxies in the high redshift universe. So we're going to be able to select them from the rest frame optical. Then in terms of spectroscopy, this is actually a simulated RF100 prism. So the advantage of near spec multi-object spectroscopy, much cleaner than the slitless spectroscopy. We don't have so much contamination. And then it's not so easy to see on this one, but we'll get the continuum, which gives us a really good shape in the Balmer break, 4,000 angstrom break region. So that gives us good constraints on ages, star formation histories. But the main thing that we'll get from near spec is going to be nebular emission lines from the rest frame optical. And that allows us to do the type of science that has been done at low redshift for years and take it way into the epoch of reionization. So we have the mass metallicity relation, it's a dependence on star formation rate. We can be probing that out to redshift 7 and beyond. And then interrogating what is the main ionizing source, AGN, shocks, star formation, and how does the ionizing spectrum from stars change as we're expecting to have larger populations of low metallicity stars. So we're going to be able to probe all of this with near spec. And then to highlight two programs with MIRI imaging in the HUDF. There's 60 hours of MIRI imaging with one. So MIRI, I was saying before, you'll get the rest frame optical to near infrared of your highest redshift objects, as well as, we lose H alpha at redshift 7 in near spec. So, okay, this one, these are both imaging campaigns, but there's also some MIRI individual object campaigns. So this isn't exhaustive. There are definitely more out there, and I haven't highlighted so many of the individual object ones. There's also an IFU survey as part of NearSpec, and you can go to the website and look up all of the approved GTO programs if you haven't already done so for your own proposals. We're past the cycle 1 deadline. I'm sure lots of people are waiting with fingers crossed. There are some proposal statistics. So there were 1,173 proposals submitted, and that's a 4-to-1 oversubscription, and around 32% European PIs. And about half of the time that was asked for was split between exoplanets and galaxies, roughly 50-50. And then the average time request was about 23 hours, but there were some large program requests. So there were some with requesting more than 100 hours. So that's all about JWST, but what will JWST not do, at least on its own, to further our knowledge of the high redshift universe? And for that, we have to take a step back, right? And I'm going to use, so here's a plot we've already seen today from Steve's talk. And he was pointing out that at the high luminosity end, we're really relying on observations from the ground at the moment. So this is going to be taken to space with Euclid just next year with the launch. So here's the footprint of the XDF. So roughly the field of view of Hubble, roughly the field of view of JWST. Euclid's field of view 3 times the solid angle subtended by the moon. And the Euclid Deep Survey will cover 40 square degrees. So that's 40 of these squares. So these are a couple of slides from Rebecca Bowler. She is the expert on this, and she's here. So, if you have more questions about this, you should connect with her. This is a slide showing the current constraints on the UV luminosity function at redshift 8, right, and where they start to run out. But with the Euclid Deep Survey, well, I should have explained first, there's 2 different possibilities for how it extends to brighter magnitudes. And there's some evidence at lower redshifts that maybe it's less of a steep drop-off, with the idea that perhaps, AGN haven't had enough time by redshift 8, redshift 7 to have done all their feedback and ceased star formation. So if we had a less steep cutoff, this is like a double power law slope to the UV luminosity function. These are the predictions from the Euclid Deep Survey, down to 26 magnitude over 40 square degrees. And these are the predictions if we had a more standard Schechter function fall off. And you can see the numbers predicted here for the different redshift bins. Euclid's going to be great for identifying very high redshift galaxies, but it has a bit of a problem when you're relying on the visible band as a dropout, because it's not so good at distinguishing the difference between these 2 types of SEDs, essentially. So this is where the Vera Rubin, by splitting up this band into the more standard sort of optical bands we're used to, you get a better constraint on the break. I just saw that my internet was unstable, so I hope I'm not cutting out. And with a 10-year survey, the depths we're looking at are sort of 27.5 in R, 26.8 in I. Help probe redshift 7.
I think you're still here. It's
I'm
a
still
little
here.
bit, yeah.
I saw everyone had frozen, so I thought I'd just wait. Okay, so this is going to help for detecting galaxies around redshift 7, so a little bit lower redshift. we're going to get all of these huge samples of galaxies, but we still want to be able to get spectroscopic confirmation. There'll be quite a long overlap, we hope, with JWST, but JWST has a limited lifetime. So thankfully, there are still some new spectrographs that are coming online. We've got the moons to be commissioned on the VLT in 2023. Fiber-fed multi-object spectrograph, multiplex up to 1,000. Redshift, wavelength 1.8 microns, which means that we'll be able to get Lyman alpha out to the highest redshifts. And then the ELT, there are two in particular, Harmony, which is a 3D spectrograph. So you can think of Muse basically, but with a massive mirror to increase sensitivity, but quite a small field of view. And then a second generation telescope is a multi-object IFU called Mosaic, where you get 100 different IFU arms. So all of these, they're really probing the rest frame UV, but with high resolution that JWST doesn't give you. So this means detailed measurements of the Lyman alpha profile and offsets due to outflows and the kinematics of the gas. And once you have mosaics, you're also looking at galaxy kinematics from the rest frame optical out to Redshift 5. We've already seen some from ALMA, from the molecular gas, etc. But this is from either stellar kinematics or the ionized gas. And this is the last slide. So sorry, I can see my time ticking away then. We can't finish this talk without talking about the Rayman Space Telescope. Think of Hubble, but think 100 times the field of view. Imaging from 0.5 to 2 microns with some spectroscopy as well. So there's still spectroscopic follow-up. No proprietary time, and it will be out to L2. And the first billion years of cosmic history survey is looking at detecting around 30,000 redshift greater than 8 galaxies at 10 sigma down to the 26 magnitude limit. So that's the end. Thank you so much. And yeah, I hope you're as excited as I am.
Thank you very much, Emma, for this review. Unfortunately, I don't think we'll have time for questions, but you'll still be around on Slack, right?
Yeah, I'll answer anything on Slack. Thank you. Cool.
Thanks very much. And now we'll have another view of high-redshift galaxies with James Webb with Mauro Sabradach. And again, I'll show you a sign after 10 minutes. Oh, you're muted, I think.
Okay, is this better?
Yeah.
Sorry about that. So thank you very much to the organizers. It's a great pleasure to actually talk science and not just talk on Zooms on many other things in life that we do right now. And these meetings are always exciting because it kind of brings us closer together as we are really sort of longing for that. Unfortunately, today, I think I'm going to be presenting more puzzles than answers, but luckily we have the shiny gold, don't call it orange. It's a shiny gold telescope that is going to be launched soon. And for the first time, it's really exciting because as somebody who's been on a GTO team for a while now, hearing every year it's going to be a year from now, made it quite daunting. But this time, for the first time, it's less than a year from now, and it really looks like it's happening. Just yesterday, we got an update that the telescope is fully folded together and stowed, and they're just doing final electronics testing, as Emma was saying, and it's a really exciting time. So what are the current puzzles about galaxies at the epoch of reionization? One of the great things that we learned about those galaxies came as we already heard previously from Mauro, came from Spitzer. Spitzer is great because it does study rest frame optical wavelengths for a redshift 8 galaxies. Here we have a bunch of different SEDs that I'm showing, just the model ones. And if you look at the channel 1 and channel 2, which are denoted in red, you can see that those different SEDs, which mainly differ by age. So one has a 300 million year old stellar population, the bottom one has 5 million years old stellar population. Those galaxies will have very different colors in Spitzer. And so if we can measure those, and if we can measure those for a particular redshift, as I'll show in a second, you can actually see old stellar population in those galaxies. Old meaning old by those redshifts. So one of the most exciting examples and one of the biggest puzzles that we got from Spitzer is MAX 1149 JD. It's a redshift 9.1 galaxy. This is the image from Surf's Up survey, and you can see this little red splotch is a galaxy redshift 9.1. And if you look at the SED, so here is the SED that we did back in 2014. You can see that the colors, I offset those two red points just so you can see the measurement is very, those are very red color. Also the 3.6 minus H color is not very blue compared to the objects that Mauro was showing to us. So it's a very peculiar galaxy. And at first, people were saying that it's probably those nebular emission lines that are contributing to these strange colors. But once the redshift was measured by Hashimoto, it became really clear that this is a galaxy with the Balmer break. This is one of those 300 million year old stellar population galaxies, which is really bizarre because the universe at that point is only 550 million years old. So we're having a huge puzzle because if you subtract 290 from 550, you get less than 300 million years after the Big Bang to start forming stars. And this is clearly not what your textbooks have been saying all along. And so it's a big puzzle, and we're wondering if this population is common, if this is just something really weird. Is this a pink elephant, right? I mean, we only have really one object so far for which spectra and colors were measured. So for that reason, my graduate student, Victoria Straight, has started to adding to this sample. And so here is one example of a redshift 10 galaxy for which, you know, a Balmer break like this would be a problematic. And this particular galaxy doesn't show it, but here is a different galaxy from her paper that is showing it. And once again, we are seeing this issue of potentially having evolved stellar population at redshift 8. I'm not saying that this is a very common thing. I'm guessing sort of 10% of galaxies are going to be showing this, but it's common. It looks like common enough that it's going to be a really interesting to see what JWST has to say about this and how old is really old. But for now, we have Spitzer data, and in Victoria's paper, you can also download the catalogs. She just got submitted the second one just a few days ago. But really, what JWST is going to be best at is, of course, spectroscopy. And even here, we are going to be for big surprises. So why spectroscopy? If a picture is worth 1,000 words, right? A spectrum is worth 10,000 pictures. So you get a lot of information from a single object. And here is a single object that it's particularly near and dear to us because we discovered it recently in our group, in my group. This is the dichromatic primeval galaxy at redshift 7, DP7. You can see a spectrum on the lower left corner. And what is surprising about this object is shown in this graph, which shows equivalent width of Lyman alpha as a function of luminosity. It's a low luminosity 0.3 L star galaxy, yet it has a 200 angstrom, more than 200 angstrom equivalent width of Lyman alpha. It's a super bright in Lyman alpha. We don't think it's AGN contribution because in that case, Lyman alpha would have been broader, but it's not. But it is spatially, we do see Lyman alpha to be spatially resolved, and we are wondering what this object is. It's not really bright enough that as a regular galaxy, it would be able to carve its own isolated bubble. So it would be really interesting to see what this galaxy is doing. We can actually measure its reionization bubble if we have systemic redshift for this galaxy, and we're of course trying really hard to get it. But spectra, of course, the next step from getting a spectrum of a single galaxy is looking at a whole population. So Lyman alpha emitters are really good in probing reionization. So here's a schematic of two types of reionization. On top, you see a late reionization, which has a lot of small bubbles. So blue is ionized, so it's blue, you can think of blue as bubbles. Whereas an earlier reionization with really large bubbles is shown in the bottom. And so if you now look at this galaxy in three slices, redshift 8, redshift 7, redshift 6, you would see that if you observe, say, Lyman break galaxies among these galaxies, you can observe the same number of Lyman break galaxies. And then you wonder, among those Lyman break galaxies, how many do have Lyman alpha in emission? And if you're in this late reionization scenario, you will get very different statistic on what you would see in emission compared to reionization that it has large bubbles. You would get a lot more Lyman alpha coming through, and you would also see a very different statistic in terms of equivalent width. So in order to do that, you of course, JWST is of course going to be fantastic because it's going to have all these capabilities of slitless spectroscopy that we are going to use. But we weren't just sitting down and waiting for JWST to happen in a year from now, all these years, but rather we embarked on a survey where we were searching for Lyman alpha emitters at redshift 7.5. And so here you see 3 examples out of a sample of 63 galaxies. We detected 3. And you also have non-detections in that very small corner, but those are the most important data, of course, is your non-detections. Here is also Lyman alpha emitters at redshift 6. So these were both taken with CAC. And when you combine all this data together and do Bayesian analysis in which you forward model the amount of Lyman alpha emitters you should see among Lyman break galaxies in different scenarios of your reionization models, you get a result that looks something like this. What is plotted here is the neutral fraction as a function of redshift. And in the red dot is our redshift 7.5 point, which is telling us that that the universe at that point has been quite neutral. In fact, the neutral fraction measured is 85%, which is a very high value. And that also, given that at redshift 6, we are seeing the universe almost ionized, that means the reionization had to proceed very rapidly. How exactly you can make reionization proceed that rapidly is a matter of debate. What we are showing here are just results from this measurement. So it's puzzling because it looks like it's going pretty rapidly, and if faint galaxies are mostly responsible for ionization, this evolution should not be as fast potentially. So we are in for a better measurement of this with JWST. We're hoping to get this number down to 10%. So as we have mentioned many times, the future is bright. It's bright because of JWST. Here is a part that I'm involved in Canucks. Nearest GTO team is going to observe 5 clusters as cosmic telescopes. So using clusters to magnify background universe. There are going to be 3 frontier field clusters, 1 relics cluster max of 417 and 1 clash cluster max 1423 that are going to be observed with NIRS and NIRSpec. Similarly, NIRS and NIRSpec observations are going to be done with ERS program that was already mentioned, and this data is going to be available immediately. So the future is bright. It's magnified by lensing. It's assisted by JWST. And I really hope that all these puzzles I have presented here are going to be resolved very soon. And the most exciting thing, however, is going to be the stuff that we aren't even thinking about now. So thank you very much, and I'll take questions.
Thank you, Marusha. We might have time for a very short question, if there is one. Otherwise, we'll go.
Yeah. Okay, so is the Redshift 7.6 point consistent with late reionization models?
Yeah, so we are seeing late and rapid reionization indeed.
Okay. How are we on time, Maxime?
I think we don't have time for more questions.
Okay.
I'll answer them on Slack. Thank you.
Yeah, thank you. Thanks very much.
So next we have David Sobral from Lancaster that's going to talk about, I think, these extreme reionization era objects.
And somehow my camera decided not to work, which is always great.
I don't see the screen so far either. Oh, it's good.
I think it's working, but my camera is not. Yeah, sorry about that. Especially because I was planning on appearing on the slides, which makes this even worse. Anyway, so first of all, thanks a lot to Alyssa, Maxime, and David for organizing. It's been brilliant. And also thanks to Maruza and Michele for essentially introducing my talk. And although I have not been resolved in the camera, what I'll try to show you is that we can go from the picture on the left, which is the past, black and white, blobology and putting slits, to looking forward to James Webb, where we will be resolving the hosts, and especially the hosts of early ionized bubbles. And Marissa already told us that Lyman alpha emitters are amazing for doing this, because by definition, if we find a Lyman alpha emitter, it is a host to an ionized bubble. That is because it's the only way that Lyman alpha can actually escape resonance. But on top of that, actually the Lyman alpha profiles, they contain a lot of information about both the interstellar medium of these galaxies, but more importantly about the CGM and the IGM. And especially with the detection of double-peaked Lyman alpha emitters, and I think even in single-peaked, we can actually use their profiles to even measure the sizes of ionized bubbles. And perhaps to illustrate what you can see is a comparison on the left from, for example, if you look at the Lyman alpha emitter when the universe is fully ionized, but is a very nice counterpart, you see that the blue wing can extend by quite a lot. So what you expect is, as you move into the epoch of reionization, essentially what will happen is the blue part will be further and further cut off until essentially you can only see the red part. But in practice, and especially if we detect the blue part of wings, and with the caveat of the importance of getting the systemic redshift, this is really, really important, we can actually use this to measure the size of the bubble. And I think this is really transformational. And of course, the question that I will try to focus on in my talk is not just about measuring the sizes of the bubbles, but it's actually on what makes these hosts so special. I mean, we can make the question of which sources reionize the universe. Here, we know that something inside the bubble reionized them. So perhaps asking the question about what's special about them is quite relevant. So maybe they produce a lot of Lyman continuum, maybe the escape fraction is high, or maybe they reside in overdensities. Now, the galaxies that I'll be focusing on, and I thank Marusa also for putting them in the plots and in the context. This is just a further placing them in terms of the full Lyman break population, and also to do with other Lyman alpha emitters. So I'll focus on Masosa, CR7, and VR7, which, even though they've all been found with these wide and deep emission line surveys, they sample quite a range of properties. So Masosa is fainter in the UV. It's actually the reddest, while VR7 is more like a typical LBG, and CR7 is something in the middle. So it's very bright in the UV, very bright in Lyman alpha. And here I'll mostly focusing on what we can already do and looking forward to the future. I think the future is obviously also multicolored and multi-wavelengths, apart from being at high resolution. But today I'll focus on what we can already do with MUSE, focusing on Lyman alpha, with Hubble at rest frame UV, and then what ALMA tracing the dust continuum, and C2, which we already heard from Michele as well. And before we go there, I think it is good to put into perspective what we would measure traditionally, which is a single number for a single galaxy. And if we do that for these 3 specific galaxies, you actually do not detect dust continuum in any of them. And specifically, CR7 is with a square, but it should be a triangle also pointing down because it is not detected. And if you actually transform the ratio between infrared and UV into metallicity, it means these are very metal poor sources in principle, and they're very dust poor as well. But I guess on the other hand, C2 can probably tell us a slightly different picture because all of these are undetected in dust, but VR7 is extremely bright in C2. CR7 is sort of in between, and Mesosa remains undetected. So I guess technically Mesosa is the only Lyman alpha emitter within these bright ones that we do not have a metal line detection yet, but it is much fainter, so it's perhaps not surprising. Now, if you move to a result view of these sources, CR7 contains these 3 bright UV clumps, which we named A, B, and C. VR7 actually shows quite a, it's big, seems like a big galaxy, although I'll show you that it's actually made of 2, and it's very likely a late stage merger. And Mesosa is quite compact, so it's much more similar to the galaxy Marusha showed from Palicia et al. It also contains kind of a redder component, which is quite puzzling, actually. But I think, as Marusha also mentioned, taking spectra is way, way better than pictures. And a spectrum itself can already tell you, for example, the difference between systemic and where Lyman alpha is coming out. So this can tell you a little bit about the IgM, and in principle, even about the Dittergat medium. But with ALMA, you can get a view of C2, and especially because for VR7, this is really bright, you can really get outstanding features with it. So there's definitely complicated dynamics, perhaps even shells, perhaps outflows going on, or more likely the effects of a sort of a late stage merger. And I think the picture only gets complete once you point the VLT with MUSE at this, and you beautifully detect this Lyman alpha halo, a redshift 6.6 from a galaxy where we have no indication of being an AGN. And then you can actually compare the UV light, C2, and also Lyman alpha. So if you do that and you look carefully at the different slices and also decompose the UV light in HST, you realize that this galaxy is very likely a late stage major merger between 2 main components. There's a lot of dynamics in it. I guess naively, you could be tempted to interpret as rotation. It's definitely not rotation. This is merging activity. And even though the Lyman alpha halo is smooth and consistent with low redshift Lyman alpha emitters, the extra kinematics surprisingly match C2, which is something it's not so easy to explain because Lyman alpha, the radiative transfer, should be very different from C2. And the velocity offsets from systemic are in general relatively low. So again, this is consistent with being hosted by an ionized bubble, but they change spatially. So perhaps it's not really a bubble, but more like a complicated carved structure within the neutral medium. And if you compare spatially how C2 and UV is changing, then perhaps this is sort of looking forward to what James Webb will reveal. And very likely we're seeing some of the first evidence for clear metallicity gradients among the galaxy, where the UV might be tracing where the population is most metal poor, and then C2 where the population is likely more enriched. And I really cannot look forward enough to seeing the results from James Webb of this. So finally, in my last 2 minutes, I would like to end with CR7 and how much we've learned over the last sort of 5-6 years, especially because if you point the VLT with MUSE in just 4 hours, you again detect this beautiful Lyman alpha halo that extends over all the components. And because you have access to 3D information in C2 and also in Lyman alpha, you can extract at different positions and really start addressing the
question about what is the nature of individual clumps, it seems like almost all Lyman alpha comes from component A, which is the brightest, but we also detect a smooth Lyman alpha halo, again, consistent with low redshift Lyman alpha emitters, and with this galaxy being in an ionized bubble. So to finish, and if you take nothing else, I guess you can't take it home because most of us are home, so it's the stay at home message, is that even though the future, and I guess part of the present is a bit black and white and not so bright, I think over the years, we've gone from blobs and slits to realizing that these sources contain Lyman alpha halos, C2 halos. They're made of different components. They're very rapidly assembling. I think the revolution of ALMA has been incredible and has really delivered on the promise of using C2 as not just a redshift machine, but actually an ISM machine almost. And that really reveals that a galaxy like CR7 that we thought was a three-way merger is more like a six-way merger at least. And perhaps there's even mysterious components within it that are producing high ionization spectrum. So I'm really looking forward to data, for example, from the GTO that will do it with NIRSpec, and also the capabilities that the community will have to study this and other sources with the IFU. So I'll leave you with the conclusions. Sorry I didn't appear and most of my plan got screwed up, but I'm sure the future will be better. Thank you.
Thank you very much, David, for this talk. Alyssa, do you have any questions apart from what I've written?
Well, may I ask a question? Well, I give myself permission. Okay, so did I hear correctly, David? Do you have velocity maps of the C+ and the Lyman alpha here, or
yeah? So for Muse, you mean for Muse and C2 for VR7 and CR7?
Yeah. Did you show those?
I showed some slices just.
Okay.
So I guess for CR7 I showed some of the slices, and I guess here you can see some of the extracts from the different components.
Yeah. This is really interesting. I mean, I was just wondering if if the velocity field across the system looked as though the two components were moving the same way. Was that what you were saying, or it was?
So I guess you could see it like this, right? So you see the redshift more redshifted than the more blue shifted components. So you see that A and B are the same plane, so it's definitely not rotation. Although if you take low resolution data with ALMA, you might conclude that there's rotation because there is a gradient. But at high resolution, it's just different clumps.
Sure. Okay. No, that's really nice. Thank you. Okay. How are we doing for time?
We have around 20 seconds, so maybe we can skip.
Okay. Let's move on.
Unless there is another pressing question, but I don't see any.
There's your pressing question.
Sure. No, maybe let's move on.
Move on. Okay. Thanks, David.
And now we have Daniel Montlock from Imperial talking about high redshift quasars with Euclid.
Okay, good afternoon, everyone. Can you see my slides?
Yes, everything works.
Okay. Great. Okay, well, thank you very much for having me here, or I am actually here in London, one of the few people who is. And the basic message I want to talk about in the next 10 minutes is that as far as discovering new high redshift quasars go, and particularly at redshifts greater than 7, Euclid is the next big thing due to its combination of area and wavelength coverage. And so I hope that everyone will be excited about that. And in practice, I hope what Euclid will be doing will be feeding JWST with targets for spectroscopy. So to give a sense of why high redshift quasars are so exciting, and I just want to check are the images of the people on the side blocking the side of the slide, because it is for me, and I just want to check it's not.
No, I think we don't see it. I think it's just the presenter view.
That's good. So this is 30 hours of VLTX shooter pointed at the first redshift 7 quasar found. And you see here what the science yield, if you can find these high redshift quasars is. Everything here, bluewood of Lyman alpha, is basically just noise, except for a couple of transmission spikes there. And everything redwood of Lyman alpha here, including these little absorption lines, etc., is all signal. So that's the point of getting these things. They're by far the brightest non-transient objects in the high redshift universe. So our current status here, summarized in this plot, which I'll show a couple of versions of, which is redshift sort of ranging from 6.5 to 7, where I think already, and especially by the time of Euclid, we've got great samples of sort of 50 odd quasars in this redshift range, but it's from redshift 7 to 9 that's the sort of the really exciting new frontier, and absolute magnitude here on the vertical axis, which corresponds almost directly to apparent magnitudes here. And it's been 10 years since we were sort of able to break the near infrared detection barrier and start moving past redshift 7. But in that time, only 8 redshift 7 quasars have been found, and only 3 of those are above redshift 7.2. So it's been pretty slow going. So that's, currently that's where the excitement is filling in this plane here. How are we going to do this? So this is a very useful, but I find admittedly confusing plot from the Astro 2020 Science white paper on this subject that Roberto already showed this morning. And what this is showing here is, the numbers obviously go with area. So Rubin gets the largest numbers of high redshift quasars until it runs out of sensitivity because it can't effectively get past or possibly even to redshift 7 because it doesn't have the near infrared coverage to discriminate between quasars and other red objects. NGST or NGRST will come along and do fantastic things and probably be the first survey to go past redshift 9 or so, but that's another 5 years hence, and it also doesn't have the greatest area, so its numbers will be limited. So Euclid lives in a sweet spot there. It's got the combination of large area, 15,000 square degrees, depths, which is not to get faint sources, but to get high signal to noise on the sources we do detect, and wavelength coverage. And so what I'm going to be talking about here is a Euclid preparation paper, where I've been involved, obviously, but really it's Rhys Barnett, who's now working in medical research, who did all the work. And so this is the take home, or the stay home indeed, message from this, is what the full Euclid survey could reasonably be expected to yield, with a reasonable verging on a pessimistic evolution of the quasar numbers. You've got the depths over here that we used, and it's just the wide survey imaging. NISP, unfortunately, for those of you who know about that, won't now have the wavelength coverage to contribute significantly to this because it won't see the Lyman alpha break. And you see here that, beyond it, Euclid will obviously also detect quasars less than redshift 7, but I think it's clear that our focus will be on following up those candidates that are plausibly above redshift 7, and you see how it will, dominate the numbers here. It's possible that the surveys, particularly the sort of combination decals, dells surveys, will put a few more points in here between now and Euclid flying, but it's unlikely to make significant progress just because of the limitations of the current data. So we did this using realistic catalog simulations, and the next thing is to put sources in at the pixel level, that's happening within the Euclid collaboration. And we can do even better depending exactly how Euclid and Rubin combine their resources. It's not at all clear exactly what's going to happen yet, but certainly there are discussions ongoing to basically share catalogs and or pixels. But you see what that will add is these larger numbers of fainter sources, which will be good for population studies. But in terms of the best targets, they will be, the Euclid data in itself will be sufficient there. So in terms of numbers, this is obviously a busy slide, but these are just tables from the Barnett et al. Paper, so you can look those up if you want. I suppose the most exciting thing here is the Euclid planned first data release in 2024, hopefully covering 2,500 square degrees. And for the current best fit to the evolution of the quasar population and a pessimistic model, these are the numbers that we get here, all above, all above redshift 7. And I guess I'm just highlighting in this box here the most exciting objects, because these would be the most distant quasars that we have. And so it would be fantastic. The brightest ones of those will be fantastic for probing both reionization and supermassive black hole growth. The overall numbers here for the full survey, I mean, it's 2029, it's a long time away, but they are fantastic. The idea of having samples of hundreds of quasars above redshift 7. And in fact, once we get to those sorts of numbers, the game will change as well, because that will then require dedicated spectroscopic follow-up if we were to follow up all those objects. I think it's unlikely that that will happen, and that the focus will be on the brightest and the most distant objects that we find. To give you a sense of sort of what that will be, this 2017 prediction here is essentially the sort of back of the envelope calculation from the approximate depth that you get before you did this seriously. And then I actually hate the color scheme of this plot. It's sort of very 70s to my eye. The sort of 70s, kitchen tiles shows the completeness from Reis's simulations. This is Euclid by itself. So, essentially comfortably getting to, 22nd magnitude in J there. This is all in AB. And then if you add in Rubin, then what that does is fills in this gap here in the sort of redshift 7 to 7.5 range, just because you have higher signal to noise, or not really signal to noise, more precise dropout measurements in the optical band. And also the optical band is narrower because it's a sharper Z band than the Euclid O. So that's the summary of what Euclid can do and why I'm excited about it. And I'll just finish here by showing another pretty picture of Euclid sitting there in orbit, and a timeline. So scheduled for launch late 2022, given that we've been talking about JWST a lot today. All the ways that phrase scheduled for launch makes you feel a bit nervous, but that date has been pretty stable for a while now. And it's got a 6-month trip and getting started out at L2. And I think it's, I at least have my eye on DR1 here in 2024 as our first target. And if Euclid flies and we get that, and we get several tens of redshift 7+ quasars and the first few discoveries at redshift greater than 8, I will certainly be very happy. And if it's allowed at that time, I will go to the pub, which I'm not going to get to do this evening, but I'll take questions.
Thank you very much, Daniel. Alyssa, do you have any questions so far?
Thank you. I would also like to go to the pub tonight. Okay, so no, this was wonderful. Thank you. And I wondered, what's your personal priority scientifically for the follow-up? Which objects are you most interested in?
It's the brightest objects we can find at, say, redshift 8 will be the winner for, I think, anything. So they will get the biggest signal to noise for the reionization studies, and hopes of damping wing as the obvious target there.
Yeah.
Personally, it's the supermassive, the evolution of the supermassive black hole population, and particularly to me, it's the envelope. So there's I didn't show one, but there are sort of common plots of a dot for every high redshift quasar with redshift or time versus black hole mass. And so obviously we're finding the biggest and the brightest, but there's a sense of sort of an envelope of the most difficult objects to find. And I suppose I want to see how that envelope goes. And of course, it would be astonishing if, again, for sort of the 3rd or 4th time, that we go through this process of saying, okay, this is the absolute extreme object, that anything we find now will be on the route to becoming what we saw at redshift 7 or what we saw at redshift 6.5. But that keeps on getting broken. And I mean, one of my favorite things there is the redshift 6.3 quasar, whose phone number I've forgotten, but was so bright that SDSS didn't find it in their early searches because it was in the 2-mass catalogs, and that was one of their criteria for not selecting, because there's no way a quasar could be that, a high redshift quasar could be that bright.
Yeah.
And yeah, I like it when the universe surprises us.
Yes, Certainly. Excellent. Okay. I guess we should move on, Maxime.
Yeah, I think time-wise we should. There might be one or two more questions in the Slack, but thank you again, Daniel. Thank you.
I'll answer the questions in the Slack, but I'll stop here.
Perfect, thanks. And now for the final talk, we have Anna Schauer, directly from Austin. So it's very early for her, I think, presenting something about the ultimately large telescope, which I interpret as a theorist's dream, really.
All right. Thank you so much. Thank you so much for having me. Yes, I'm tuning in from Austin, so it's morning here. It's now 9:30, so not too bad, but yeah. So I want to talk today about the very far future. And for that, I'll just put up this timeline of the evolution of the universe again. And the area of research I'm usually interested in is redshift 10 to 30 roughly, where the first stars are forming. And to access this redshift regime, I use numerical simulations and semi-analytical modeling, like almost everyone who works in this redshift regime does. This area can't quite be accessed yet with direct observations, so even James Webb won't be able to see like really small clumps of first stars. It can be accessed with a global 21 centimeter signal, so that is great, but that also doesn't give us the opportunity to observe individual first tiny galaxies, so-called mini halos. And of course, we can see the CMB very far away. So last year we had a fun project where we asked ourselves the question, what kind of telescope would you actually need in the very far future to observe those mini halos, those population 3 stars? And we defined 3 criteria that are needed that we can actually observe those stars. One is we need to have enough sources in our field of view. So we need to have a sufficient number density of sources in the sky. 2, we need to actually see those sources. So our population 3 stars need to be bright enough that we actually see them. So a telescope needs to accumulate enough light that we can actually detect those POP3 stars. And the third one is that we detect those stars unambiguously, so that we don't accidentally just observe a bunch of brown dwarfs and say we finally found POP3 stars, but that there's really a distinction between the different sources that could be those population 3 stars. So I'll walk you through my 3 criteria in this short talk. Because everything is simulation based and semi-analytical based, that's what our input is too. So for the number density of sources, we went to the 2 most recent papers in the literature where population 3 star formation rate densities were predicted. And then what we did is we took those and then we translated those models into how many star forming sources are there per volume, assuming a typical number of stars per halo and a typical lifetime of such a population 3 star. And this then can translate into an expected number density of sources on the sky, which you can see in the bottom left panel here. And what you can see is those numbers that you can see here for all redshift ranges for 2 different models. Those numbers are quite high. This number is per square arc minute. And as a comparison, James Webb has a field of view of 4 arc minute squared. So just per 1 arc minute squared, even if we take the lowest model, we can see quite a number of sources on the sky. So we're good in terms of we will find enough sources even with a small field of view. The next thing is the brightness of such a population 3 star cluster. And we have many, many unknowns. So we don't know the exact number of stars or the total mass of stars. we have to assume an IMF or a mass distribution of stars. If it's like smaller than like a real big cluster, then we can assume a few stars. And then those can have different properties. And one property is especially interesting, namely if the star cluster has some nebular emission. So because we don't know very much about those first stars, we will assume different models to, so to say, have a variety of models, and to be safe that with like a variety of those models, this telescope would pick up a signal. That's what we do, and therefore we agreed on that we assume that for a fiducial model we have 1,000 solar masses in stars total for a fiducial star cluster, and we assume a distribution of those total stellar mass, and as a standard deviation we pick Harvard X. So 67% of all star clusters have masses between 300 and 3,000 solar masses in total. And then we choose different stellar populations. So we choose a model that is more towards the POP2 side, where we have a low mass IMF that ranges from 0.1 to 100 solar masses with a group IMF. We choose a model of just population 3 main sequence stars. And when you talk about those high mass stars, it doesn't really matter anymore if you have if you have 3 100 solar mass stars, or if you have 1 300 solar mass stars. So we can kind of normalize that. That makes the model very handy. And then we choose also a very massive SED for population 3 stars between 50 and 500 solar masses. And we choose 2 different nebula fractions of 0 and 100%. Like, it's a short paper, so we don't go to every single model that is there, but we make sure to, so to say, have one of every kind. Then we have those fluxes, and we put them through the NIRCam filters for our 3 different models. For the main sequence stars, so the several very massive population 3 stars, the extreme IMF from 50 to 500 solar masses, and the more present day-like IMF between 0.1 and 100 solar masses. And you can see that we pick up a different amount of flux. On the left, I showed in nanojansky, and the right in the AB magnitude. As a comparison, we have here the NIRCam limits. We can see in NIRCam we go down to a limit of 29th AB magnitude. Unfortunately, that's far not enough. That's not even on my plot. So in order to observe those population 3 stars, we need a limit of roughly 39th magnitude in F200, in the F200 filter. Then when we look at how does this actually look like in our color magnitude diagrams, what I show you here is F100 versus the F100 minus F200 filter. You can see that for the more massive models, we pick up a lot of our sources. For the POP2 like IMF, we pick up still a little bit of those sources. And we found that when we have a filter combination of F150, F200, and F444, that leads to the best results. So this slide is about contaminations. So how does it look like in color space, and what contaminations did we consider? So you can see here that when we have this filter combination of those 3 filters, they occupy different regions in our color diagram. And what we can find here on the left are brown dwarfs. We found out that brown dwarfs have a lower number density on the sky. And we pick up a few of the brown dwarfs in this color model, but not many, because those are only the brown dwarfs that assume that they are extremely cloudy. So we don't know how many of those brown dwarfs will actually be there, but it will be few, and they will only occupy a small overlap fraction. And we can rule out, for example, population 2 sources by looking what moves out of a lower wavelength filter. So we say it's pretty unambiguous, the detection that we can make. What kind of telescope is therefore necessary? And for that, we go back to a paper from about 10 years ago, presented by Roger Angel et al. And a telescope that is ideal to observe those objects has a diameter of roughly 100 meters. It needs to be extraterrestrial, so one could go to the space, but one could also build it on the moon. And probably in a few decades from now, or several decades from now, technology will have further advanced. And we think it would be cheaper to have, instead of a full mirror of 100 meters diameter, to have a rotating liquid mirror, because it requires less material to be transported either in space or onto the moon. So with those properties from Roger Angel's paper, we see it fits exactly our case. And this is my attempt to put a paper into one slide. So yeah, I would like you to leave you with this for my conclusions, and also say thanks a lot for the organizers. This was a very nice conference. It was a very nice break from normal work time, and yeah. Thanks for having me present here.
Thank you very much for coming.
So we might have time for one quick question.
Yeah.
I just love the idea of a 100-meter telescope on the moon, but maybe later.
Maybe later, yeah. Okay, I think we will imminently be removed from the room, so let's proceed quickly. I did wonder if I can ask, this is really fascinating, but what about the number densities and confusion with slightly brighter things that might be in the way? Is there an estimate of how that would look?
So I think the slightly brighter things, like this is, I think, as faint as you can go in terms of sources. Like there's no stars that are further away than those POP3 stars. So I think we can rule out a lot of sources because they are brighter. Like any small galaxy that in the ionized universe will be way brighter than 39th magnitude.
Okay, so okay, which raises different problems, I suppose.
Yeah.
Okay, but anyway.
Thank you.
Yeah, thank you.
And I look at that too, so thanks a lot.
Stop here, and I'm going to leave Alyssa to give the closing remarks. Then.
My closing remarks. Well, my main closing remarks are to thank everybody a huge amount for coming and participating. So I personally can't wait to watch all of the talks back in a slightly less frantic situation and actually take in what everybody had to say, which I think will be really good. So the RAS have been recording what we said. And for people who don't want to appear on YouTube, I think you've already told me, but if you feel very strongly, then tell me again, because I'll be in charge of editing the final cut before things become public. Yeah, and I think that's going to be really fantastic. The Slack will stay open, so please continue chatting in there. I think that's been very successful. And just shoot me emails about any problems or anything else. Finally, thanks again to the RAS. I'm not sure if Lucinda is currently here or not, but I know she and Richard and many of the others have put a lot of effort into organizing the infrastructure for us today. And thanks to Maxime and David, who've done a wonderful job organizing. Okay, so let's end there. Goodbye.